your own option if you would like.
Dave, where can folks find this?
I put it in the chat.
Hey, Dave, you probably should just keep posting it in there because all the people joining after you posted it won't be able to see it.
Okay, it's fine. Well, it looks like
Dave, I'll also definitely mention it in my intro.
Yeah.
Slide about
well,
it.
It looks like I'm the last post there. Well, Todd's just reposted it, but yeah, should be.
Yeah, literally my chat was empty. So
Oh, really? You don't see the chat before?
yeah, no, it was empty until just now. Until Todd just
Yeah. As people come in, they get a fresh chat window.
That's right.
So, yeah, right.
Yeah, so it makes sense to post it again in first thing.
Every minute.
Maybe not every minute.
Okay.
Can you vote more than once? Like, can you keep reloading it? And...
That's a good question. Actually, I don't know how the Google Forms work that way. So I thought it was sort of by email, but yeah, I don't know. That's fine. We're just like Chicago politics here. Vote early, vote often.
Yeah, I just submitted a response and you get a little thing saying submit another response. So you can just keep.
Okay.
Yeah. So if you really want to.
Right. If you really want to bump something up, then I guess, yeah, go for it. Like I said, vote early, vote often. Yeah, I can tell, Marika. How many have you voted 3 times already? So
Have I? Well, I don't know who the one vote was before. That could have been me, actually. I'm not sure. So, Dave, can you see names associated with the votes?
Good question. I don't think I do see names, actually. So
Right.
I was just teasing because it was like CI's prediction and predictability is leading the way. So I thought, oh, well, Marika's voted. So
Oh, I voted for more than one thing. Well, I'm going to run and grab some more water, but I'll be right back.
Great.
Jan, is the code of conduct slide the one right after this one?
Yes, correct.
Perfect. Thank you. Just double checking.
We're up to 37 people.
Hi, Dave.
Hi.
Can you hear me well?
Sorry, what's that?
Can you hear me well?
Oh, yes. Yeah, absolutely.
Okay, thank you.
I see we also have the Wiley William Large.
That's right. I'm awake, David.
Never
Never miss a chance to listen to you guys.
Did you watch the hockey game last night, Bill?
Parts of it, yeah.
Yeah. What was a
I
nail
definitely
biter?
did.
Huh?
I definitely did.
Yeah, that was a nail biter.
I know.
Salut, Patricia.
Hey, Dave.
No, with the hockey games in the Euro 2000, it's quite a week.
Yeah, my team Belgium is playing in an hour and a half, so
Oh,
I'm getting nervous.
yeah.
Oh, come on. They're looking
Oh,
good.
This is much more important, of course.
Oh, I get it. Jan. That's why you were sick, right? But
That's why these kind of sessions are so good. You can have the game on and just, session. It's terrific.
I agree with Jan. The Netherlands will play soon as well.
Yeah.
Tomorrow, is that tomorrow, Rene, right? Or I'm not sure actually.
Now, in the Netherlands, it will be tonight, but for me, it will be tomorrow. Due to the time difference.
Boy, they squeaked by that last one. They squeaked by that last one, didn't they? That was pretty lucky.
Yeah, it was a bit,
Bit tense.
lucky. It could have been better, so to say.
Okay, everyone. I think it's time to get started. There we go, recording in progress. So this is being recorded. Welcome, everyone. This is the Polar Climate and Land Ice Working Group session. My name is Jan Leenaerts. I'm from the University of Colorado Boulder, and I'm co-chair of the Land Ice Working Group together with Bill Lipscomb. And then we have co-chairs Marika Holland and Hansi Singh, and also our wonderful liaisons, Aldis Duvivier, Dave Bailey, and Gunther Legee. So in name of all of them, welcome to all of you. Good morning, good afternoon, good night, depending on where you are. First of all, this is a session within the CSM workshop, and we pledge to respect the code of conduct from the UCAR. So please be respectful to one another and look at this very important code of conduct. We pledge, all of us, to adhere to this code of conduct. And please take a look at the diversity website of UCAR if you want to know more about UCAR's efforts in.
Actually, I've just posted the full PDF of the code of conduct in the chat.
There we go. Thank you, Hansi. So next up is a really important item for this morning. We're trying to, even though this is a virtual meeting, we're trying to make it interactive. So as the last part of our session from 11:30 to noon Mountain Time, we're going to have breakout sessions, and you can choose your favorite topic for the breakout session by going to the discussion topics Google form that is posted several times now in the chat. So all of you should be able to click on the link and choose your favorite topic. So there are options already there. You can also choose your own topic of choice. So add a new one. And apparently you can vote multiple times to keep it interactive and going. So this form closes at 10 a.m. at the end of the break, which is also our poster session. So you have time to vote on your topic, and we'll see after 10 a.m. we'll see what topics are most popular and choose from those, and then form the breakout room. So we'll come back to this later in the morning, and then we'll also have Google Docs to share notes, to compile notes, and to share them with other groups at the end of the session to really compile all our ideas and share them with you after the meeting. Okay, so this is schedule, at least the first part of the schedule. So we have 4 blocks, the first of which starts in 2 minutes, chaired by Bill Lipscomb. And then we have the poster session and the break, half an hour from 9:30 to 10, chaired by Hansi Singh. Then we have 2 more presentations, so oral presentation blocks. One starts at 10, and then the last one starts at 11. And then the last block is the one with the breakout sessions. And then after the breakout sessions at noon, we also have a separate lunch, which is very informal, for the polar climate and the land ice, because we thought, being together is great, but also having smaller separate groups would also be very nice. So I think that's it in terms of the schedule. What I do want to give away to the speakers is that, and this is something we've communicated before, that you have 8 minutes. You will be reminded that you have 1 minute left after 7 minutes. So please make sure you keep your time to 8 minutes. And then we have 2 minutes for questions and answers, and also for speaker switching. If you have your slides on your screen ready and you're comfortable sharing your screen, please do when you give your presentation. But if you prefer us to share the slides, please send them to the convener of your session, and they will do that for you. So that's also an option. It's up to you, whatever you prefer. If you have questions for the speakers, please raise your hand, which is a Zoom feature. I'm sure all of you know how to do this now, or type in the chat, and we'll keep, as conveners, we'll keep we'll keep track of questions and ask them afterwards. If there's no time in the 2 minutes, we can also try to reserve some time at the end of each block, depending on how the time goes. Okay, so Hansi, is there anything else you wanted to add?
Thank you, Jan. Yes, there's one final thing, and this is regarding computing. So many of you have reservations or have chatted with us about running on the Polar Climate Working Group computing allocation. And so we would love to see the CPU hours burning and the machine humming. So if you are scheduled to run and you have not yet started your run, please either talk to us about any delays that are going on, or get your run started. So if you need help getting your run started, Dave Bailey is awesome and amazing and there to help facilitate it. So please do that, because we want to be sure that GoCon doesn't take away our allocation. Okay.
Okay, thank you, Hansi. I'll give the virtual floor to Bill now. Have fun, everyone. And if you have any questions for us, logistical, please put them in the chat as well. I'm happy to help. Thank you. Enjoy.
Thank you, Jan. And I will go ahead and introduce our first speaker, Renee Weingart, who will be speaking about understanding and improving the representation of mountain glaciers in CESM. If you'd like to go ahead and share your screen, Renee.
Yeah, okay. I think it's better, wait, oh, I can do it. Oh yeah, no, it's better if you do it for me, because I have some issues here, if it's possible.
Do I have the latest copy of your talk?
Oh, I sent it to Jan and Elizabeth, so.
Okay, I should have a copy here. Let me just open it up.
Okay, if you wouldn't mind sharing, Todd.
And what's the name of it? Because they all have different looking names. What am I looking for?
Okay, it's called LIWG CESM Workshop, and then 06/2021.
Okay, I see that one. One moment, please. Okay.
Thank you, Todd.
Sure.
And Renee, I will, as Jan mentioned, I'll give you a shout out when you're 7 minutes in. At that point, you can wrap up, and we'll leave a couple minutes for questions.
Okay, and let me just change to slide mode. Okay, does it look okay? Oops.
Yes, very good. Okay, I will start quickly as possible. Okay, my name is René. My presentation will be about understanding and improving the representation of mountain glaciers in CSM. First of all, I would like to thank everybody who contributed to this project so far. Next slide, please. I will give first I will start with a short outline. I will start with scientific goals. Then I will give a short introduction on the High Mountain Asia Grid. And then I will go into more detail on the representation of mountain glaciers in CSM, mainly focusing on glacier surface mass balance, variable elevation profiles, and updating the CLM glacier dataset. Next slide, please. Okay, the main goal of this project is to find out what the capability of an ESM with a regionally refined grid of 7 kilometers will be in the simulation of the surface mass balance of glaciers in high mountain Asia. Main reason for this is because most ESMs and GCMs are not able to capture glaciers, and that is why it would be interesting to find out whether we could do it with a variable resolution model. The next question will be to find out whether this regionally refined grid can improve the simulation of seasonal and perennial snow in high mountain Asia, and what the impact would be on the regional refinement on the simulation of hydroclimatic variables. Next slide, please. Do you hear me? Yeah, okay, thank you. Oh, and there happened something with the figure, but never mind. I will start, introduction on the high mountain Asia grid. So we started more than a year ago with developing a grid for high mountain Asia with a 116-degree refinement over the high mountain Asia mountain ranges and the Tibetan plateau included. In order to be able to simulate surface mass balance, we had to define a new glacier region, which is covering the high mountain Asia domain. And we used the same settings for Greenland as well as for Antarctica, but the difference is that we have a maximum snow depth of 1 meter. That is actually how we started. And further, we decided to use a 36 elevation class scheme with 200 meter elevation bins each. Next slide, please. The main outcome of the first simulations that were completed last year was that the surface mass balance we simulated, that it delivered quite a negative surface mass balance. Unfortunately, too negative, especially over the southeastern part of high mountain Asia. There was, however, also some positive side thing, and that is that over especially the southern parts of the high mountain Asia, as you can see in the inlet, that there were some regions where a positive surface mass balance was simulated and glaciers can in fact grow. But still, however, we still wanted to find out how to improve the negative surface mass balance. Next slide, please. So because of that, we did several experiments and sensitivity runs, etc. And based on that, we were able to do several tunings. The first is that we increased a maximum snow depth from 1 meter to 5 meters in order to allow for more refreezing capacity. We increased the bare ice albedo to have less ice melt. And we widened the rain snow repartitioning, which is in close agreement with observations over high mountain Asia. Further, we used Adams variable resolution tunings on cloud cover and sea ice to correct underestimation cloud cover over high mountain Asia. And that goes a bit too fast. And we turned off the long wave radiation downscaling. The most important thing is that we did also a new spin-up, more spin-up approach. And so far, we were able to improve the surface mass balance significantly, as you can see in the lower row figures. And also the number of grid cells, for example, where a positive surface mass balance is simulated, is now quadrupled. Next slide, please. In order to understand more, especially over what was happening in the southeast, we went more into the model, also looking on grid cells and to see also the elevation, the variable elevation relations. And as you can see, what we found out is that for the surface temperature, that we found some temperature inversion above around 4,000 or 5,000 meter altitude. Also, we found that, for example, for the lower figure where you can see the surface mass balance, iceflakes figure, that there's a very negative surface mass balance. I choose that grid cell for your information, but this is mainly probably because of the glaciers that have ended up lower than actually where they're supposed to be. I will go into that later. Next slide, please. So in order just to start with the temperature inversion, we want to find out whether it is a real thing or whether it's some kind of model issue. But actually, it's not. We found out that what is happening is that when you go to higher elevations, that that at some point a snowpack starts to develop due to better conditions for the snowpack. And this increases the surface albedo, which results in a decreased net shortwave radiation and a faster decline in ground heat with altitude. The second thing is that the snowpack functions as an insulator for the underlying soil and therefore causes soil temperature inversion, which you can see in the lower graphs, but also in the table where you can see that if you move from elevation class 16 to 17, where there's a change in snowpack, that there's a 1 Kelvin increase in soil temperature, which is equivalent to the surface temperature you saw in the former slide. Next slide, please. Then about the surface mass balance and in relation to the glacier elevation. So what we also found out was that especially over the southeastern part of high mountain Asia, which shows in the upper left figure, is that there's some discrepancy and that the elevation difference between glacier and grid is very high. In some regions, the glaciers end up 2,000 meters lower than the grid cell mean elevation. And I know for this region, the glaciers are supposed to end up at around 4,000 or 5,000 meter altitude, but they end up around 3,000 meter altitude, which therefore can explain the large amounts of ice melt. The reason for this discrepancy is that there are some inconsistencies, inaccuracies in the glacier outlines of Randolph Glacier Inventory version 1, version 2, relative to Randolph Glacier version 6. But also there are some likely uncertainties in the globe topography. And further, the glaciers that are there in the former data set, so in the data set that is usually used, there are only 61 elevation bins of 100 meter each, where the last one covers 6,000 meter till 10,000 meter altitude. But that means that we are missing those glaciers that are there between 6,000 and 7,000 meter altitude, and that we also miss some part of the accumulation that can eventually
time to wrap up, please, Renee.
Yeah, I'm almost finished. Potentially, it can increase the surface mass balance. So we wanted to know we thought, okay, it's time to update the CLAM Glacier dataset, and we did it based on the Randolph Glacier Inventory version 6, BED machine version 3, version 2 for the Greenland and Antarctic ice sheets, and we used the 30 ArcSec GM TET, which is all more consistent with what is already used. Unfortunately, I was not able to complete it entirely. It is still going on, but I can show you these figures. The upper figure shows the glacier fraction for all the glaciers from the Randolph Glacier Inventory, and the lower figure shows the glacier fraction for the BED machine of Greenland and Antarctic ice sheets that are derived from the BED machine. And actually, that is about it. That was my presentation. The next slide is thank you. So, okay.
Thank you very much, Renee. Dave Lawrence has a comment in the chat. Dave, would you like to just summarize what you put there?
Just wanted to say that within CLM context, we've been playing, Sean Spencer has been playing with a precipitation downscaling, simple one that seems to work well. So more snow or precipitation at higher elevations and less at low elevations, which might also help with your surface mass balance. I don't think it was included in the original downscaling that I think you developed, Bill. And the second thing is that with the hill slope model, we are accounting for slope and aspect, and again, probably pretty critical for glaciers, mostly on north-facing slopes, right? So I think we could have a conversation.
These are very positive developments that can for sure help us to improve the surface mass balance. Yeah.
All right. Time to move on to our next speaker. Thank you again, Renee.
Yeah, thank you.
If you could stop sharing, and then
Yeah.
our next speaker, David Bonin, can start sharing.
I think Dot is sharing, but anyway. Yeah,
Okay.
thank you.
Oh, right. And Dave, could you go ahead and tell us about transient equilibrium responses of the AMOC to global warming and coupled climate models?
Yeah, thanks, Bill. This is work that I've been doing with my advisor, Andy Thompson at Caltech, as well as Emily Newsom, who's a postdoc at the University of Oxford, Shantang Sun, a postdoc at Caltech, and Maria Rugenstein, who's at CSU. And so really, because this is the CSM workshop, I thought it'd be great to kind of highlight behavior that's going on in CSM and contrast that to a different model. So what you're looking at here is just two different model simulations as part of Long Run MIP, which has been collected by Maria Rugenstein and Jonah Block-Johnson, and it's really just used to study century and millennial timescale atmosphere ocean processes. So this top panel is just showing the maximum value of the meridional ocean overturning stream function in the North Atlantic for CSM and CNRM, in which CO2 was abruptly quadrupled. And what you see is that both models exhibit kind of a weakening of the AMOC on this kind of centennial timescale. In CSM, there's this abrupt, partial recovery of the AMOC, and then there's this kind of slow, gradual re-strengthening of the overturning circulation. And then in contrast, CNRM kind of weakens on that centennial timescale as well, but then really stays prolonged weakening, has a prolonged weakening or even a collapse of the overturning. And so just this plot below actually just shows a Hofmüller plot of the depth of the stream function in CSM, and this is in the North Atlantic. And again, you see that weakening in conjunction with the shoaling of the overturning. And then there's this gradual deepening and re-strengthening of the overturning in CSM. And then in contrast, CNRM barely recovers and begins to show more of a recovery towards the end of its simulation. And so really what I want to try to highlight today is, can we identify and understand processes that influence the transient and equilibrium responses of the AMOC to warming and coupled climate models? And so to do this, I'm going to kind of actually borrow some language from more theoretical literature from Nikarashian and Ballas in 2012 and Malte Janssen's work with these idealized toy models of the ocean's overturning circulation. And so what they say is that you can relate the stream function to the density gradient in the North Atlantic and throughout the basin by assuming that there's no flow at the base of the ocean and there's no flow at the surface. And so from this, you can back out a stream function. And I've kind of just schematized this here on the top panel, which these are the isopycnals in CSM, which remain relatively flat throughout most of the basin. And then they outcrop towards the North Atlantic. And so here's just that density gradient flipped. Sorry for the sign here. And I can back out a stream function, just assuming the boundary conditions are 0 at the surface and the bottom, which is denoted here in purple. And you can see that compared to the stream function that you get from CSM itself, it matches both the depth and the structure and the magnitude of the AMOC as well. And so we think that this might be a good way to kind of diagnose what's mechanistically going on in these two different models. And just to convince you more that this works really well, here's that same time series in black of CSM's overturning strength in the North Atlantic. And in purple is just the scaling as if I diagnose the density profiles throughout the entire basin and in the North Atlantic and reconstruct that overturning. And you can see that it captures both the weakening, that partial recovery, and that gradual strengthening, although it tends to underpredict the weakening. And so then we've done this for all the models that we did in the study. And I've just calculated linear trends through different 150-year periods in these models, just to show you that in black is the GCM's diagnosed stream function, and in purple is this scaling. And you can see that it captures both the intermodal spread and really the tendency to show a weakening and then a slow gradual recovery of the overturning in these models as well. And so to kind of highlight, what's going on in these models, I'm just going to focus on 3 different phases. The weakening phase, which is centered at that 100-year time scale, that partial recovery phase, which is a couple centuries after the weakening, and then this re-strengthening phase, which is over the next 1,000 years. And so this top panel is just showing the density gradient change in these two models. So CSM on the left, CNRM on the right. And you can see that they both tend to show a weakening of that density gradient in conjunction with the weakening of the stream function, and here in purple. And then these middle panels and the bottom panel are just showing the density change in the north and the density changes in the basin, partitioned into density changes due to temperature and salinity. And so what you can see is that they tend to show more weakening in the north, largely due to a warming of that water column with some kind of input from freshwater as well. And then the basin, it just tends to warm more with this kind of formation of some salinity anomaly that begins to show. And so then the models agree on what they're doing on this weakening phase, but once you go to the recovery phase, you see kind of different behavior. You see in CSM, the stream function begins to recover slightly, and same with that density gradient. And this is somewhat driven actually by positive salinity anomaly that forms throughout the subtropical Atlantic and then is kind of advected towards the North Atlantic. But CNRM tends to show more of a weakening of the stream function and a weakening of that density gradient, which is largely due to the fact that there's just this high latitude freshwater anomaly that begins to form in the North Atlantic. And so then finally, when you get to the re-strengthening phase, you actually see that there's a positive anomaly in the stream function and a positive anomaly in that gradient for CSM. And in CNRM, you actually see the opposite. You see it still stays weakened. And so what largely controls this strengthening phase on this time scale is the fact that the basin warms more relative than the north. And so then this density change is actually a bit greater than the density change throughout the North Atlantic. And that's driven by this low latitude warming signature right here. And then there's this kind of slight role for the fact that the salinity anomaly in the North Atlantic is positive here, and it's fresh here in the CNRM model. And so to kind of schematicize what's going on here, this is the Hofmahler plot of salinity, just say between the 1,000 and 2,000 meters in CSM, and plotted over that is actually our annual Arctic sea ice area. And what you can see is that the salinity anomaly forms when the AMOC is weakened, and then slowly throughout the simulation, it gets advected up into the high latitudes, and it begins to erode that freshwater anomaly due to sea ice melt or an intensified hydrologic cycle. And then in CNRM, you actually see that freshwater anomaly is really large in the high latitudes, and it really overpowers that salinity anomaly, in which there's just this really large signature of freshwater in the high latitudes. And so what we've done with these models is just calculated a linear trend about that AMOC recovery time period, and calculated the remaining sea ice extent in these models. And you can see that they're fairly highly correlated, in which a model that has more sea ice left tends to have a stronger recovery, and a model that has lower sea ice left tends to have a weaker, little to no AMOC recovery. And so just as a summary of this, there's a schematic of what's going on here. These two models are very similar on the weakening timescale. So this is a strong AMOC recovery and a weak AMOC recovery. Through those first 100 years, they both weaken largely due to a high latitude temperature increase. But in CSM, that large partial recovery is really driven by the fact that there's this salinity anomaly that is advected into the high latitudes, and the fact that the low latitudes warm, which increases that density gradient. In CNRM, you see the same signature of low latitude warming, but you see this freshwater signal in the high latitudes that prevents that salinity anomaly to reinvigorate that deep convection. And then on this longer time scale, we've noticed that these models are very similar, in which the low latitudes begin to keep warming, and that really drives a stronger overturning that's even stronger than the initial strength. And so just to kind of provide some more mechanisms, the long run MIP has been a MIP of opportunity. So there's a lot of output that really isn't available. So it's been hard to kind of diagnose specific mechanism what's going on here. So in the most recent times, I've been trying to develop a conceptual model of the ocean's overturning circulation. And I would say this is kind of the canonical view that everybody has of the ocean overturning, in which there's buoyancy loss in the high latitude North Atlantic. That water sinks, it flows adiabatically back towards the Southern Ocean, where it upwells along isopycnals. It's transformed and it goes back towards the higher latitudes. And then you also have this lower cell here. And so what I've been doing is I've been saying that, okay, we can keep track of temperature and salinity evolution equations in each basin. So the Atlantic, North Atlantic, and the Southern Ocean, which are going to be a function of some surface forcing here, some diapycnal mixing.
Time to wrap up, please, Dave.
Thanks, yeah, and some advection terms. And we can relate these two. I'll wrap this up very quickly, and actually just build a more conceptual model of what's going on here. And so I actually forced this model with a specific warming scenario, where it was 4 degrees of warming in the North Atlantic, 2 degrees of warming in the basin. I can talk about this more later if people are interested, but you actually do see the signature of that salinity anomaly form in the basin, and how it gets advected towards the higher latitudes going forward. And so, yeah, this is work that's been written up into a paper for Journal of Climate, and I'm currently trying to write up the conceptual model for another paper. So thank you.
Thank you, Dave. Do we have any quick questions?
So this is Peter Gent. Can I make a comment?
Go ahead.
There are examples of a couple models where the AMOC has recovered after several thousand years. So I think that if that CRNM integration went further, it would have recovered. And there's some from Manabi and Stauffer and another. And I talked about them in a paper I wrote called a commentary on the AMOC stability in climate models, if you're interested.
Yeah, no, I'm aware of that paper, and I agree. I think that if CNRM was run out to 6,000 years, you would actually see a slow recovery. Maybe not a full recovery, but definitely one. Yep.
Cecilia, do you have a quick question?
Yes, hi Dave, great talk. I'm curious what you think might be the freshwater source in the non-CESM model. I forgot what it was.
Yeah, it's been hard. The freshwater fluxes in the output we have aren't specifically partitioned into sea ice runoff or like a hydrologic cycle. But that's the motivation for the kind of this conceptual model, is to maybe provide a little bit more mechanisms of that. But I do know that CNRM loses its sea ice more quickly than CSM. But it does also have a lot more runoff, I believe. The hydrologic cycles are very similar between the two models, actually. So I would assume that there's something going on, at least maybe from ice sheet melt in Greenland or something like that. Yeah.
Okay, thank you again, Dave. We'll move on to our next speaker, Lili Ren, who will be speaking about source attribution of Arctic black carbon and sulfate aerosols and Arctic surface warming during 1980 to 2018. Lili, are you able to share your screen? Great.
Yeah.
Also, there's a comment from Julio in the chat. So Dave, if you could take a look at that.
Dear everyone, I'm Lili Ren from Nanjing University of Information Science and Technology. I'm going to talk about source attribution of Arctic black carbon and sulfate aerosols and associated Arctic surface warming during 1980 to 2018. The Arctic has warmed rapidly since the 1980s with a 1.5 K increase in the surface air temperature, which is about 3 times faster than the global average. A number of studies have examined possible mechanisms that cause the rapid Arctic warming. Observations and modeling studies suggest that variations in aerosols are a good explanation for the faster Arctic warming. In this study, we use the Global Aerosol Climate Model CAM5 equipped with an explicit aerosol source tagging to examine the attribution of Arctic aerosols to 16 different source regions, such as Europe, North America, South Asia, East Asia, Russia, and the Arctic. All the physical, chemical, and dynamical processes of aerosols for each target source region are considered independently and consistently by using additional sets of aerosol variables in CAM5 East. The sulfate concentration shows a considerable decreasing trend from 1980 to 2000, which then slows down after 2000 year. The decrease in sulfate during this time period results from the reduction in emissions from Europe and Russia. It contributes to 19% of the decline of the Arctic sulfate concentrations. The average concentration of black carbon in the Arctic shows a decrease of 23% in 2014 to 2018 relative to the 1980 to 1984, mainly due to the reductions in emissions from the Arctic and Russia, which make up 9% and 15% of the decrease. We also study the changes in source contributions to the annual mean vertical profile of sulfate and black carbon concentrations over the Arctic between 2014 and 2018. And 1980 and 1984, below 6 kilometers due to the effective emission reductions. The contributions from both Europe and Russia to the Arctic sulfate was decreased. Between 10 and 15 kilometers contributions from South Asia and East Asia increased at the upper troposphere, which is consistent with the increase in emissions over these regions, leading to a combined increase in sulfate concentration at the upper troposphere of the Arctic. The black carbon concentration below 2 kilometers contributed by Arctic and Russia emissions each had a decrease, which dominated the decrease in black carbon concentration in the Arctic's lower atmosphere. Similar to sulfate, black carbon concentrations contributed by East Asia and South Asia increased in the higher altitudes. Both sulfate and black carbon increase in the Arctic climate by perturbing the atmospheric and surface radiation balance. The Arctic sulfate exert a negative radiative forcing due to aerosol radiation interactions, primarily by scattering incoming solar radiation back into space with the forcing in the range of minus 0.4 to 0 water per square meter. The atmospheric black carbon can absorb solar radiation in the atmosphere, leading to a positive radiative forcing due to aerosol radiation interactions of 0.1 to 0.4 water per square meter in the Arctic. Previous studies have suggested that the Arctic climate responds not only to local Arctic forcing, but also to outside forcings due to the meridional energy transport change. To estimate the relative roles of regional aerosol trends in affecting the Arctic warming, we looked into the temporal variations of annual mean radiative forcing of sulfate and black carbon in different latitudinal bands during 1980 to 2018. We can see that within the Arctic, the magnitude of sulfate radiative forcing due to aerosol radiation interactions decreased from minus 0.21 water per square meter in the 1980 to 1984 to minus 0.1 water per square in 2014 to 2018, indicating a warming effect in the Arctic from the local sulfate change. Over the middle latitudes, the sulfate radiative forcing due to aerosol radiation interactions decreased from minus 0.87 to minus 53 water per square meter. This positive black carbon radiative forcing due to aerosol radiation interactions increased from 0.55 to 0.74 water per square meter in the middle latitudes. Then we apply Arctic climate sensitivity factors to calculate the recent Arctic surface temperature change related to the variations in sulfate and black carbon radiative forcings over the different latitudinal bands in the right figure. As mentioned above, due to the decrease in sulfate and at middle latitudes, strengthened meridional heat transport caused 0.06 K Arctic warming, and we can see that the combined total effects of sulfate and black carbon produced Arctic surface warming of 0.3 K. Last, this is the summary. The decrease in sulfate and black carbon concentration were mainly due to the reduction of emissions from Europe, Russia, and local Arctic sources. Increase in emissions from Southern and East Asia lead to positive trends in Arctic sulfate and black carbon in the upper troposphere. Changes in aerosols over the middle latitudes over the northern hemisphere have a larger impact on Arctic temperatures in other regions. through enhanced poleward heat transport. Next, the combined total effects of sulfate and black carbon produced Arctic surface warming of 0.3 Kelvin. That's all. Thank you.
Thank you very much, Lily. I don't see any questions yet in the chat. Do we have any questions for Lily?
I don't have a question. I just have a quick comment here. If you're not speaking, can you please mute yourself? We've heard some background noise during the talk. Thanks.
That Dave with a question?
Yeah, sure. So it's interesting that you were saying about the partition of aerosols from terrestrial sources and local sources in Arctic. So did you sort of categorize which ones are more important, the local sources? I mean, and I assume you're talking about ships when you're talking about local sources.
Lily, did you hear the question?
Sorry, my network is not well. Yes, the emissions from South and East Asia lead to the positive trends in Arctic surface and black carbon. But as you said, the emissions from the Arctic dominated the black carbon concentrations in the lower atmosphere. It is up to the different kilometers and atmosphere.
Thanks. Right. Thank you very much, Lily. Yu Chao, are you online?
Yes, I am.
Okay. I have your talk here. I'm going to go to full screen.
Okay.
And just let me know when you'd like me to advance.
Okay. Thanks, Bill. My name is Yu Chao Liang. I'm a postdoc at Lamont, and this study is working with Lorenzo Povani and Ivan Mitevsky at Columbia University. So I'm going to speak about the Arctic amplification and its seasonal cycle in response to abrupt CO2 forcing. Next. So this is Arctic amplification. I think everyone knows it. Arctic warms, then the rest of the globe. Okay. Next. Some previous study tried to study the drivers of Arctic amplification. And next, please. And most of them using, for example, doubling CO2 or at the most 4 times CO2 experiment. However, in the future, the CO2 concentration could be even higher than 4 times CO2 relative to pre-industrial concentration. For example, on the right panels in SSP5, 8.5 CO2 projected scenario in the future, you can see that at the end of 21st century, the CO2 level is about 4 times CO2 relative to pre-industrial level. However, during 2200 and 2300, the CO2 concentration could be as high as 8 times CO2. So in this study, we further want to explore what is the Arctic amplification change in different levels of CO2 concentration. Next, please. So the scientific questions, next, please.
Sorry, it's not advancing.
Oh, it's okay, yeah. So the scientific questions we want to answer here is how the Arctic amplification in response to different, oh, I'm sorry, yeah. So the Arctic amplification also shows some seasonal characteristic because it is dominated by different mechanisms during different seasons. So if we just look at the annual mean Arctic amplification, may be somewhat misleading. Next, please. So the scientific questions we want to answer here is the how Arctic amplification in response to different level of CO2. And the second, we want to address is seasonal cycle change in response to different CO2 concentration.
Sorry, I'm trying to advance. It's not working.
Oh, really?
I'm going to stop sharing and launch it again. Sorry about that.
Okay, yeah, sure. So yeah, I can keep speaking. Yeah, so the methodology we are using is that we are using Ivan Mitalovsky, the recent published GRL paper in which he run abrupt CO2 simulation with different level of CO2 from 1 time CO2 all the way to 8 times CO2. Okay, and this run is conducted for 150 years. And we also look into corresponding slab ocean model simulation with 60-year simulation. And the CO2 concentration is given from 1 time CO2 to 6 times CO2. And we'll only focus on the last 30-year mean values. So, okay, yeah, Bill, maybe you don't need to full screen. Oh, it's okay, yeah.
I've gone to a different program. It seems to be working better.
Okay.
So where let me know when you'd like me to stop.
Okay.
Bill, we're still at the title slide.
Bill, we
Yeah.
still see only the
Next,
title
yeah.
slide, nothing else.
Oh, sorry. Okay.
So let's go next. Yeah. Please go to. Is it working, or please go to slide 7.
Okay. I pressed resume share. I'm so sorry, Yuchao.
It's okay. It's okay. Yeah, it's all right. Yeah.
Hey, Bill, I got it up right now if you want me to do mine.
Yeah, please take over. Thanks.
Yeah, okay. Thanks. Yeah. So here just what I say. Yeah. So the methodology we use fully coupled simulation and slab ocean model with different CO2 concentration forced. Okay. Next, please. So here's the Arctic climate response in response to different CO2 forcing. So on the panel A, we see surface air temperature response for fully coupled model and the slab ocean model. And as expected, the temperature response increases as a function of CO2. Next. So you may see there's an abrupt drop. There's an abrupt drop in the 4 times CO2. This is caused by the AMOX slowdown, which has been discussed in Mitalovsky et al. 2021 GRL paper. And this may also relate to what Dave Bonin just presented. Next. And correspondingly, the CIS loss increases as a function of CO2. Next, please. So, and correspondingly, we also see that the turbulent heat fluxes from the ocean to the atmosphere also increases. So this is possible that these 3 components are highly coupled with each other. It's more Arctic warming, and more CIS loss, open more waters, allowing more heat from the ocean to the atmosphere. Next. So after more heat into the atmosphere, you also thicken the Arctic tropospheric air column. Okay, next. So now we focus on the annual mean Arctic amplification, which is defined by the Arctic temperature change divided by global temperature change. So in panel A, you can see the evolution in each abrupt CO2 experiment. So roughly speaking, about 70 to 80 years, this Arctic amplification reached quasi-equilibrium state. Next. And you can see in the bottom left panel, the scatter plot also shows the characteristic of Arctic amplification. And in panel C, next please. In panel C, we see the Arctic amplification factor actually decreases as a function of CO2. And this is not surprising because we noticed that in previous study, we show that in a nearly ice-free condition, and similar to here with strong CO2 forcing given, CIS albedo effect and the CIS installation effect are virtually inactive. And this may lead to weaken the Arctic amplification. And this study, and also here we found the seems like the sea ice condition is the key that can reflect how strong the Arctic amplification it is. Next, please. So now we move on to our focus to the Arctic amplification seasonal cycle in response to CO2 crossing. So on the left panel is the Arctic temperature response in this last 30-year mean seasonal cycle. And I colored in blue is 2 times CO2 and colored in red for 8 times CO2. So as you can see, the peak of the Arctic warming shifted from November to December and January from 2 times CO2 to 8 times CO2. Next. And correspondingly, we also see this peak shifted of the Arctic amplification from November to December and to January as CO2 concentration increases. Next. So this we also see similar seasonal shift in slab ocean model. And we further dig into the possible mechanism for this. And we see this the turbulent heat fluxes and the sea ice loss response are also show this seasonal shift. But we don't see the radiative, the short wave and the long wave component contribute to this sea ice shift. So this is corresponding to what we saw in the annual mean Arctic warming. Is probably these 3 components they highly coupled with each other, and here that shifted the seasonal cycle. Okay. Next, please. Next. And you may wondering our experiment, it might be somewhat idealized, but what could happen if we prescribe more realistic, for example, semi-6 scenario greenhouse gas forcing? So on the top 2 panels, I'm showing the CS1 large ensemble, exactly the same model we use in the product CO2 experiment. And in panel A, you can also see this shift as time advances toward the end of the century. The correspondingly on panel B, you can see the peak of the Arctic amplification also shifted from November to December. And the next, and this is not just a model dependent feature, because also see in GFDL CM3 large ensemble, these shifts also clearly shows. And then we also look into 40 semi-6 multi-model means, although the shift is not as clear as single model, but we still see this seasonal shift tendency. Next, please. So just briefly summarize. So Arctic warming response seems like closely coupled to sea ice loss and the surface turbulent heat fluxes with as a function of increasing CO2 crossing. And the strength of Arctic amplification actually decreases as a function of CO2. And the peak phase of Arctic amplification tends to shift from November to December or January, depending on how strong the CO2 forcing it is. We are not only seeing our abrupt CO2 experiment, but also seeing in a more realistic semi CO2 or greenhouse gas forcing scenario. And these results have important implications for Arctic ecosystem and the commercial shipping. Okay, I'll stop here, and I'm willing to take any questions. Thank you.
Thank you very much, and thank you for your patience with our technical difficulties.
Okay.
Do we have any questions for Yu Chao? Cecilia? Yeah.
Hi, Yu Chao. Nice talk. I'm curious if you have an idea which of the feedbacks is responsible for the slowdown of the increasing, or well, the lack of, how do you say this? The weakening of the response with increasing CO2. I have a suspicion, but I'm curious what you think.
Right. So I haven't analyzed each feedback, like separate like albedo feedback or Lapser feedback. But here, as I mentioned, so it seems like the dominant component is the coupling between sea ice loss, surface temperature, and the turbulent heat fluxes between ocean and the atmosphere. So this probably, is the heat exchange that dominates this seasonal shift. But I also look into the radiative, the short wave and the long wave radiation, although I just look at the net surface component. But seems like this short wave and the long wave component does not show the seasonal shift. So I need more analysis to confirm, but I guess probably the local air or ocean atmosphere heat exchange dominate these processes and produce the lake.
Thanks. You certainly convinced me of that for the seasonal cycle. But good. I'll be looking forward to hearing the final.
Okay, thank you.
Results.
All right, thank you again. Our last speaker of this session is Walter Meyer, who will be speaking about an updated sea ice concentration climate data record for long-term hemispheric and regional trends and variability. Are you able to share your screen, Walt?
Okay, thanks. Can you see that?
Yep. See it, great, thanks.
Okay, and still see it, presentation mode here. Okay, yeah, thanks. I know we're running a little behind, so I'll try to make this quick. And this is a little bit different than the other talks here. I know this is a modeling workshop. And I'm a bit of an interloper here with observations, but I just wanted to present, and I want to thank CSM and Jan and the organizers for allowing me the opportunity to present on a new version of our climate data record that I think is useful for modeling applications. And so I'll just kind of quickly go through and present this. Folks may be aware of this already. This is the sea ice concentration climate data record. It's officially a NOAA product, NOAA to NSIDC product funded. The specific development of the CDR is funded through the NOAA NCEI, but it's based on NASA and the NASA DAC product. So it's kind of a joint NOAA-NASA effort. Originally, we developed this in 2011, and it was limited as far as the CDR to 1987 to present, to the SSMI and that should say SSMIS part of the record. We did include the NASA data sets that included simmer going back to actually 1979 or late 1978. But these didn't have the full transparency and the processing reproducibility that the CDR requires. And it's a combination of the NASA team and Bootstrap algorithm. I won't go into the details of that. And there's QA and QC uncertainty fields. And the new version, I hoped it'd be out by now, but we keep running into little glitches and kind of delivery things, but it should be out by next week. So just an example, this is your typical passive microwave. It's 25 kilometer daily fields and monthly fields for the Arctic and the Antarctic. And then this just is an example of the standard deviation field. And that's something that we provide based on the standard deviation of the NASA team and the Bootstrap concentrations in a spatial, like a 3x3 grid cell area that gives an indication of the relative uncertainty. It's not an absolute uncertainty, not a quantitative uncertainty, but it'd be potentially useful for weighting the observations versus, for example, models. And you can see the highest uncertainties tend to be near the ice edge. This is in March. In the melt season, you also see high uncertainties within the ice pack, or higher uncertainties because of the melt ponding and surface melt. The major enhancements I kind of alluded to earlier. The main thing that we did is we added the simmer part of the record, the early passive microwave sensor, which started in late October of 1978 and went through August of 1987 or into August of 1987. That had not been included before because it had never been processed at NSIDC and hadn't been processed really by anyone since the early 1990s. And that data has a lot of issues with it. It takes a lot of finessing to work with that data because it's early sensor. The technology was not as good. There were a lot of sensor issues with it. But we've managed to put that together and put it into the CDR without any manual QC. Goddard, when they created their record, they included simmer, but they basically did a lot of manual QCing, going through image day by day, image by image, and manually taking out or correcting data, which was not tracked. So you don't have any provenance on that. We still have some bad days that we did remove because the data was just too corrupted to use. But by and large, we were able to include almost all of the simmer record. It's in the NetCDF format. We updated some of the metadata for that. We also, we have valid ice maps, which are used for QCing the data to remove ice where there isn't any ice possible. And we took those from monthly to daily, which makes for a little bit smoother and a more finer QC there. One of the other big thing we did is we added spatial and temporal interpolation. This had been done with the NASA Goddard products as well. For small scattered missing cells, we interpolated at the brightness temperature level, which then feeds into the algorithms. For larger areas where there's missing swaths or missing days, we do an interpolation of a temporal interpolation from up to plus or minus 5 days. And so that gives us much more complete fields. And it also allowed us to basically create daily SIMR fields. SIMR only operated every other day for the 1978 to 1987 period. Even in the Goddard fields, there's only data every other day. But we used a temporal interpolation and interpolated to those missing days. So there's daily fields for virtually the entire record, except for a few missing periods where there's longer data gaps. The well-known one is December 1987 to January 1988. July 1984 also had some corrupt data and a few other days here and there. And then we also filled the pole hole in the Arctic with a pretty basic interpolation. That's something we might look at more in the future, but it gives you a complete field. You don't have a missing pole area to deal with. And then just a comparison of the extents here. Comparing the CDR with the Goddard, the two algorithm products, the NASA team and the Bootstrap. The CDR is most closely related. It's a combination of both, but it matches more closely with the Bootstrap. So the NASA team has larger differences, but there's some offsets in the way that we process versus the way that Goddard process. But overall, they're pretty small. There's not a lot of bias there. There's a little bit in the SIMR period in the Southern Hemisphere, particularly. That's still a difficult thing to handle. But again, we have data that we didn't have before. And overall, it's I think, pretty consistent with the Goddard product. So I think it's a suitable long-term data set. This is September of the Arctic. The trends are almost the same, very small differences. Some other months have a little bit bigger differences, but they're pretty consistent between the CDR and the Bootstrap, as well as the NASA team. I left that up here for clarity. So just to conclude, this version 4, which again is going to be out, it should be out next week. It's a near complete, long-term, consistent sea ice concentration record. I think it's suitable for model validation, comparison, and simulation. And there's the website for those. You can go and register and see. You'll get a notification when the update is actually made, and get regular updates. And there's the new real-time version that's updated daily, that's ongoing as well. And again, supported through NOAA, the NCI CDR program, and the NASA ESDIS through the DAC. So I'll stop there and hopefully finish up on time.
Thanks very much, Walt. Fantastic data set. Do we have any questions for Walt? Let's see. Don't see anything in the chat. Anyone like to raise your hand?
And I presented this at AMS a couple of weeks ago at the AMS Polar meeting, so I think some people may have seen it there. So apologies for the repeat, but
oh, no worries.
Appreciate the opportunity to present it to this group as well. So, and folks can feel free to email me for further questions or information about the data set.
Okay, Jan.
Hi, Walt. I have a quick question. So why is it more important to fill the pole hole rather than keep it to missing data, since it seems like the quality is, probably worse than at lower latitudes?
Yeah, it's a good question. We chose the pole hole fill. It's in response to users basically, where they basically wanted data everywhere, and so we provide that. Now it's just a basic, simple. It's the high Arctic, so there's not a lot of variability, and we don't know exactly what the variability is. So it's just an average of the surrounding days. That is, and I should note that all the interpolation, all the filling, and everything is all flagged. So if you don't want to use that data, it's very easy to denote that flag as a poll hole and take that out. So it's there to be flexible for users that want that.
Thanks so much.
Right, so we'll go ahead and go to the break now. We will reconvene for the next session of talks on time at 10, so our break will be a little bit shorter. Hansi, would you like to tell folks about how the break will go?
Yes. So the break is going to be a little interesting in the sense that please take a break, but there will also be posters. So let me tell you what posters are going to be available. So 3 folks are going to have posters. Rajashri Datta will present on the variable resolution CESM over the Antarctic domain and tell us about an initial evaluation. Kevin Rader will tell us about the CAM6 DART ensemble reanalysis, as well as data sets for machine learning that come from this. And then Elizabeth Hunke will tell us about the CEIS consortium and advancing CEIS modeling. So these 3 posters will be available in breakout rooms, and we invite you to go to these breakout rooms, check out the posters while you're taking a break, and then reconvene here in about 20 minutes, it looks like. So that's it.
And also
go to these breakout rooms.
I haven't opened them yet.
Todd will open them very shortly.
I had set them up for random, but would you like me to change that so people can go from room to room?
I think it would be great if people can go from room to room so that they can choose which one to go to.
Let me see if I can adapt that.
Okay.
Okay.
I think also, Dave, were you planning to put the survey results up in this room just so people can see where things stand with that?
Yeah, sure. I'm happy to present in the main room with that. And then I guess, I'm not sure what time we were going to close it, but we're going to close it soon. So
yeah, I think just maybe 5 minutes before 10 or something so that we can look at the results and make a decision on how we're going to do the breakout rooms after at the end of the meeting.
Yep, I posted the link and I'm now about to share the results.
Okay, and so, yeah, I guess take a break and hopefully in a couple minutes the breakout rooms will be available and you can go check out those posters as well.
Yeah, I'm going to open them now, and then you may get sent to a room, but then you should be able to leave that room and go to another room. So we'll see how that works.
Awesome. Thank you, Todd. That'll be great.
And the form is still open for those who want to vote. Please do.
That's right. I haven't clicked the little button yet that turns it off. So.
Dave or anyone, are you seeing the breakout rooms? Are you able to enter them?
I'm sharing my screen.
Okay.
I did just get an invite to the one breakout room.
Yeah, it only lets me go to one breakout room, Elizabeth.
If you and then one, let's see. But if you go back out to the breakout room menu, do you see the list of rooms and there's a join button next to them?
No, only the one that we've been assigned to.
Okay. I'm going to have to close the rooms and reopen them, okay? Okay, sorry.
Hey Todd, once they get closed, I'll take a peek and see if about that setting to allow them to go wherever.
I clicked the box saying allow them to go to different rooms, but apparently it didn't work. Okay.
Thanks everyone for your responses. It's we have pretty good turnout so far. CI's prediction predictability is still well in the lead.
Okay, Ryan, I'm going to recreate those rooms now.
No. You don't need to recreate them. I just will check the box to allow them to choose a room.
Yeah, I did have that checked, so.
Okay, so we should be all good now. I'll open them back up real quick.
That seemed to work.
Ryan, I just got an invitation to join one particular room. I don't see how I would choose based on what's on my screen.
So if you hit cancel on that and then open up the breakout rooms tab at the bottom, you should be able to hover over the number next to the breakout room.
That works for me. So now I can see a list and I can choose.
Because Bill, that's just the one you were in before, so it was trying to stick you back in there, but you can
Got
hit cancel and then.
Yeah, I think if I hover over each one, it goes to join, so I should be able to do that.
Cool.
Yeah. Thank you.
Yep.
I'm just going to take a quick break, but I'll be back in about 5 minutes.
Dave, do you know what time we should close the rooms?
We should close the rooms probably about 9:55.
9:55. I'll give them a 2
Yeah,
minute.
it doesn't give people a lot of time, but I think that we want people to start coming back around 9:55 to start for the next session and stuff. So,
okay, thanks.
Yeah, but.
Hey, Dave, Alice D wants to do a quick screen share test before we get started for the next one. That's fine.
Okay. All right. I can stop sharing for.
No, you're good right now. We're gonna wait until about like 9:50, 9:55 to do it. So
Yeah. Okay, that's fine. I'll be back shortly.
Okay. Yeah, I can stop your screen share anyway, so no worries.
Oh.
Dave, are you here?
Yeah, I'm here.
Okay.
Need me to stop sharing? Yeah.
No, I think it's fine. I'm just trying to figure out how we should split up the breakout rooms.
Right.
It's like there's interest in all of these, and then there's a couple added on with like, land, ice, and polar, and then Greenland.
Right. Yeah. I think those two we could just add into sort of one of the other discussions.
Yeah, I guess.
And then
maybe we should like diagnostics maybe could be something relevant to all of the different breakout groups.
Yeah, that's true. Yeah, absolutely.
Just ask people to discuss those. Greenland is a little, but only one person has said Greenland. So
yeah. I think that, you could maybe just sort of, if there's time, people could throw that into the future projections of Antarctic change. People could maybe, so.
Or the variable high resolution. I was going to ask, I want to test with Ryan screen sharing since that was kind of weird the last time. Do you guys mind if I do that?
Go ahead.
Yeah, since you ask a couple of questions real quick, I'm going to close all the rooms now. So people are going to come back in. And then Dave, would it be most helpful if you just sent me a list of the names of the rooms? And then I'll create the breakout rooms.
Yeah.
Yeah, we also need to know which of us is assigned to each of those rooms. So Dave, if you want to do that, if not, I can.
Well, I think we, again, are we going to just let people sort of go between the rooms?
Right.
Maybe?
I mean, which of us? Which
of us? Oh,
yeah. We have a moderator, note taker,
okay.
One of us, so that like Jan knows which room he has to go moderate.
Right. Yeah.
Are you guys seeing the presenter view or the presentation view?
Presentation.
Great. Okay. That's all I wanted to check.
Okay. I'm going to go ahead and close the responses. I think we're stuck at 32. So
I'll be right back.
Todd, I'm going to send an email about the breakout rooms.
Great, thanks.
I'm sending you the link to the responses, so let me know if you see that. And then, so I'm guessing based on the responses, we should do all 6 of the main topics, and then we can sort of combine the extra 2. So,
I'm sorry, create all 6 and then another one with 2?
No. We'll just cover the other topics in those 6. So, okay. So I mean, you can maybe create 8 breakout rooms too, but just leave the other 2 as just open discussion or something. But all right, so the breakout leaders.
Welcome back, everyone.
Okay, Alice, which of the two would you most prefer? The stakeholder integration, historical data sets?
The stakeholder integration or the historical data sets?
Yeah. Or we can combine those. It's fine.
How many people or how many roughly people do we think it would be if they're combined?
If they're combined, they'll be about 19, which is the same as the CI's predictability.
But also, a lot of people picked more than one room, and so I'm sure people will be bouncing. So I think those numbers are not the number of participants.
That's true. That's true. Yeah. Yeah. So I don't know. We can still leave those separate if you want. I
mean, if you combine them, that's fine. If I had to choose, I'd probably know more about the stakeholder integration. I've thought more about that recently than.
Okay.
I'm not sure exactly what historical data means. Like Hansi said yesterday, is this whaling logs, or because I know nothing about those.
Right.
So we'll get started with the talks in just a minute. So we're in the process of setting up these breakout rooms. Thanks everybody for answering the survey and giving your input. It looked like there was interest in all of these topics. So we'll probably set up a breakout room for each topic, or we might combine the historical data sets, indigenous knowledge, and stakeholder integration and communication into one room. There were a couple of additional topics that people put in. One was on diagnostics. And so because there was only one response requesting that, we just suggest that diagnostics be part of the conversation in all of the breakout rooms. And then another was on Greenland. And I know that a lot of the variable and high resolution modeling work with like refined regional CAM is focused on Greenland simulations. So we just encourage you, if you're interested in Greenland, to go to one of the land ice related and perhaps the high resolution modeling group. So I want to make sure we stay on time because we do have a tight schedule. So we're going to get started here with our second set of talks. As in the earlier session, every speaker has a 10-minute slot, but we want you to do an 8-minute talk. And so I will cut you off at 7 minutes or tell you to tell you to finish up at about 7 minutes. And so without any further ado, and for those of you who don't know, I'm Marika Holland. I'm one of the co-chairs of the Polar Climate Working Group. So we are going to go ahead and get started with Molly Wieringa talking about data assimilation applications for Arctic sea ice. So Molly, if you're able to share your screen and go ahead.
Yeah, can everybody see, hopefully not the presenter version?
It looks great.
Okay, wonderful. Great, well then I will get started. Hello everyone, thank you for having me. I'm really excited to be here. I'm a second-year student at the University of Washington, and I'm excited to talk to you about kind of the beginning of our team's efforts to improve 21st century estimates of Arctic sea ice thickness, variability and change in particular, through a data assimilation application. I'd like to start by acknowledging the rest of the team that's helping me do this, my advisor Cecilia Bitz, and doctors Alec Petty and Andrew Roberts at NASA and Los Alamos National Lab, respectively. I'd also like to acknowledge the folks at NCAR who have been really helpful in getting this project off the ground, as well as support from the University of Washington and from NASA. To contextualize what I'll present today, our interest in this problem is really motivated by a desire to understand recent and future sea ice change. We want to be able to make better forecasts of sea ice and to have a more accurate record of how sea ice thickness has changed under anthropogenic warming. Some of this motivation can be explained by this figure, which shows 3 commonly used sea ice thickness products: ISAT in royal blue, Cryosat-2 in teal, both with an uncertainty bound, and then Biomass, which is a reconstructed product in the dashed black line. While Biomass does a decent job of capturing the trend of sea ice thickness over time and is continuous over many decades, several decades, its variability doesn't line up with the satellite products. And it's well known to underestimate thick ice and overestimate thin ice. We suspect that this is at least partly because biomass is constructed by merging sea ice concentration measurements into an ice ocean model, which has been shown to have a limited effect on reducing the sea ice thickness bias in models. So we believe that we can address kind of our two wish list items in our forecasting challenge and our reconstruction problem by improving by assimilating sea ice thickness data into a fully dynamic sea ice model. So our long-term goal is to produce a new sea ice thickness record from the early 2000s to the present day. The work that I'm going to present today is a far cry from that goal, but it builds the foundation for eventually reaching it. So to build a framework and an intuition for how data assimilation works with sea ice, we've been testing its efficacy with observing system simulation experiments, or OSSIs. OSSIs are perfect worlds in which the observations being assimilated are taken from a random model integration themselves. So as such, we consider them perfect, the observations, and the model itself to be by construction able to reliably sample the sea ice state. This approach removes several potential sources of error in the data assimilation framework, and it allows us to examine kind of the best case scenario for sea ice thickness assimilation. So we assimilate perfect observations into an ensemble sampling of the sea ice state using an ensemble adjustment Kalman filter method, which is integrated with the Los Alamos sea ice model through the data assimilation research testbed that's hosted by NCAR. And these experiments require us to sample the state using ensemble methods to then observe that state by creating synthetic observations from the truth, from our randomly selected truth, and then to localize our assimilation, forecast forward, and evaluate the impact. We sample the state using a 30-member ensemble of size 5. The model is configured using a slab ocean and a JRI 55 reanalysis atmosphere. All 30 members are forced with the same data atmosphere, and the variability in the ensemble is generated by perturbing parameters in the sea ice model directly. Following work done by Yangfei Zhang in 2018, we perturbed the snow grain radius and the compressive ice strength, which manifests as albedo and ridging effects in the model. We then randomly select one of those ensemble members to be our truth, and the figure that I'm showing for the ensemble here on the right, the ensemble mean is shown in red, and our randomly selected truth member is shown in blue. And so as you can see, our truth is systemically lower than the ensemble mean in these experiments. And so we infer that the ensemble in this perfect world is biased high. It's worth noting that this result would change if we'd chosen a different truth, and since our ensemble is by definition reliable, we use bias here to describe mostly just the room for improvement that could be acted on by data assimilation. So the majority of this room for improvement is located in the Beaufort Gyre, and we'll keep an eye on that region for our results. And that applies to both the spring season and the fall season. We observe the state by using the truth integration to mimic real-world satellite measurements. So this mimicry is crude in our experiments, but it captures the daily domain of the ISAT-2 satellite, which is the newest sea ice thickness observing system. The available ISAT-2 along track data for April 15th in 2019 are shown on the left from open altimetry, while the pseudo tracks that I generated by sampling along the model grid from the truth member are shown on the right. We ran a number of experiments assimilating different numbers of these pseudo tracks. So the darker colors on the figure just represent the first assimilation, while the lighter colors represent additional tracks that were added in each experiment. We assimilate a single day of these pseudo-track observations into the ensemble using a localization of 700 kilometers, so limiting the effect of that assimilation spatially. And we chose 700 because it was shown to be the length scale of a sea ice thickness anomaly. And then we assimilated that on April 15th and then also on October 15th of 2019, attempting to capture the impact of the assimilation in times of both ice loss and ice growth. We then turned off the assimilation after those single day additions and forecasted the model forward as normal. And we evaluate the results using a root mean squared error metric, comparing the ensemble that has been assimilated into to the truth member. The results for the spring forecast are shown here. So to just kind of orient you to the figure on the top row, I'm showing you the root mean squared error on day 45, on the bottom row at day 75. The first column is a case with no assimilation. The middle column is if we assimilate just a single track, And then the third column is if we assimilate the full 15 tracks across our spatial domain. And you can see that as we move from the left to the right on this figure, as we assimilate more data in a single day, our root mean squared error drops notably, which is good. We like that. And then the other interesting thing to kind of pull away from this figure is if you look at this one track assimilation case, there's a notable reduction in root mean squared error at day 45, but that effect is really lost by day 75. So there's an advantage to incorporating more data because your reduction in root mean squared error will be persistent through longer times, which we can look at a little more specifically, just looking at the 15 track assimilations for a longer integration. I'm showing you the time series of that integration on the top right, where the green is the ensemble mean unadjusted, the red is the truth member, and then the blue is the ensemble after it has been assimilated into. And I'm showing you the spatial distribution of root mean squared error at 5 time slices along this integration. And we find that the minimum root mean squared error occurs in midsummer for the spring assimilations, approximately 90 days after the assimilation itself, which is shown kind of here in panel 3. You see we've reduced down to less than 0.2 meters root mean squared error. And while we start to get some of that bias back as we move forward in the integration, the 250 days after the assimilation is still a drastic improvement over the unassimilated case. So to kind of wrap up, yeah, very briefly, thank you, Marika. Our main result is that in a perfect world, assimilating a long track Arctic sea ice thickness estimates persistently reduces model bias for approximately 3 months, and it still improves on unassimilated cases for up to 8 months, could potentially be longer. I stopped the integration at the end of 2019. And then next steps, we're looking at doing sequential day-by-day assimilations and experimenting with realistic errors by testing some direct assimilation of the sea ice thickness distribution. And then eventually we will also transition from these perfect model experiments to real-world data. So with that, thank you. I appreciate the opportunity to speak. I'd be happy to take any questions, and I'll just put the summary slide back up.
All right, are there any questions? We have time for, yeah, Gunther.
Hey, I was wondering if there's a computing cost with the increasing number of simulations that you do.
So there's not an increased cost to the number of observations being assimilated. There is a cost to running Dart with CESM and with CEIS, given that the adjustment happens in the restart files for the model. So there's a lot of stopping the model, adjusting it, restarting it. And so there is a high computational cost to doing this kind of online assimilation, and a lot of files that get output and need to be managed. So there's also a big storage management aspect as well.
So I think in the interest of time, we're going to move on. I see Dave has a question. So Dave, if you could put that in the chat for Molly, and also there's a couple other questions in the chat for you, Molly. So you could take a look at those. So thanks for a great talk. So we will move on now to Abby Smith. And Abby, if you can share your screen. So she's going to be talking about improving model satellite comparisons of sea ice melt onset with a satellite emulator. So thanks, Abby.
Thanks, Marika. Can you see my screen okay?
Yep, it looks great.
Okay, great. Yeah, hi everyone, I'm Abby Smith, and as Marika said, today I'm going to be discussing model satellite comparisons of sea ice melt onset with the satellite simulator. And I am at the Research Applications Lab at NCAR now, but most of this work was done as a final part of my PhD thesis that I recently completed. So happy to be back and getting another chance to talk about that and see the Polar Climate Working Group again. So thanks for having me. A little background on Arctic sea ice melt onset. The timing of melt onset, which we typically think of as the first time each year that we have water collecting in the snowpack or on top of the sea ice. That timing has been shown to be a useful metric for evaluating thermodynamic sea ice processes in both an observational context and for climate model assessment. However, observational melt onset products are derived from satellite observations of brightness temperatures, which are not currently simulated by climate models. And so that means that model definitions of melt onset tend to be based on other model variables that are sensible but vary, such as snow melt or surface temperature. So the impact of that means that model definitions based on different model variables end up capturing different processes. So what I'm showing here is an example from the CESM1 large ensemble, and the red line are the observed melt onset dates for each year, and the blue line down here is one ensemble member of melt onset using a thermodynamic ice volume tendency definition, as well as the ensemble spread. And then we have surface temperature and snow melt definitions, as well as an additional ensemble spread of surface temperature melt onset. And what we see is that that volume tendency definition that is impacted by ice melt is dominated by bottom melt and tends to occur earlier than melt at the surface. And this is a Pan-Arctic mean, but that's particularly true where warm water is entering the Arctic from further south, causing those melt onset dates to be particularly early. But the surface-based definitions such as snow melt and surface temperature tend to fall closer to the observations, but slightly earlier than observed melt onset. So what we can see from this is that no one model definition is exactly capturing the satellite observations of the melt onset. And in order to directly compare models and observations, we really need to be using the same definitions in order to assess if these differences are due to a model bias or actually just due to different definitions of the melt. So this diagram that I'm going to step through is going to kind of serve as an explanation of our approach and methods. And what we're doing is we're actually introducing a satellite simulator to produce the same quantities of brightness temperatures in the model that are observed by satellites. And we're doing that by using the ARC-3O satellite simulator that was recently developed by Clara Burgard and Dirk Knotts at MPI. And we have adapted that to run with the CESM2 JRA 55 ocean ice hindcast. So really trying to get at a close as possible representation of what the satellites would be seeing by using that reanalysis atmosphere. And so what this enables us to do is actually create simulated brightness temperatures that we can then compare to observed brightness temperatures. It also gives us the opportunity to create a new metric, and we're going to call this the earliest snow melt estimation. And the great thing about this new metric is that it's a slightly simpler version of the next big step into processing those brightness temperatures. And it also is a definition and a metric that we can apply to both the observations and the simulated brightness temperatures in the exact same way. So kind of removing that uncertainty due to definition differences. And while we have these new metrics, we can also compare them to the most current method of comparison, which is to use satellite-derived sea ice melt onset products that are brightness temperatures that have been processed through different algorithms, and various algorithms exist, and comparing those to what I mentioned before, which is melt onset dates derived from other model variables. So not only do we have these new metrics, but we can also compare them to what we were doing before. And you'll hear me refer to those satellite-derived sea ice melt onset products as continuous and early melt onset. So it's a lot of different metrics of melt, but hopefully we can step through it kind of quickly and it'll be relatively clear. What I'm showing here is that new metric that I have introduced that we can apply to both the simulated and observed brightness temperatures in the same way to produce earliest snowmelt estimation dates. And that is shown for two different satellite products, the DMSP as well as AMSR. And then on the right is the earliest snowmelt estimation dates from the CESM2 JRA 55. And what we see is that while the patterns are relatively similar, there are parts of particularly the central Arctic and some of the marginal seas that have earlier melt onset in the CESM2 than in the observations. If we remember those definitions of melt onset that I mentioned before, we can apply them to the same data. What I'm showing here is just an example from 2003. And we see a definition based on snowmelt and one based on surface temperature, and the comparison that we would have done before to those algorithm-derived melt onset dates from the satellite observations. And what we see here is that we typically have earlier melt onset dates across the Arctic in the model than
Did Abby freeze up for others as well?
Yes, she did.
Oh, sorry, can you hear me?
Yes, you're back.
Oh, okay.
We lost you for a minute there. Or
okay, what was the last thing that I said? Can you remember?
Well, you were talking about the differences in the comparisons of the kind of traditional way of doing it versus your, and that they showed earlier snowmelt onset or earlier melt onset. Yeah.
Thanks, Rika. I didn't mean to be on the spot. That's great, thanks. I think where I left off was probably just making the point that what's great about these more direct comparisons is that you can actually feel more confident that we can diagnose a model bias. So we haven't changed the direction of the bias or made it go away by introducing this new metric. We can just more confidently categorize it as a model bias since we've removed that uncertainty due to definition differences. One thing I'll mention before wrapping up quickly, and this is just an example from one grid cell of the evolution of brightness temperature from January through June. And we can see that the simulated brightness temperatures in red tend to closely follow the observed brightness temperatures over this time period. And so that gives us confidence that what we're representing in the model is what we actually are observing on the ground using these satellite observations. And since we have this similarity, what we can also do is to leverage other model variables to inform what these changes in brightness temperature actually mean. So there is uncertainty in these retrieval algorithms that process brightness temperatures into melt, as shown by a Bliss et al. Paper in 2017. And so we have an idea of what these brightness temperatures represent, but that's difficult to verify. So this is kind of a cool example of how models can help inform that when we have direct comparisons. And what we see is those satellite algorithm-derived dates tend to fall after substantial snowmelt has occurred in the model. And if we wanted to actually quantify that, we can calculate what I'm calling here the normalized snowmelt, which is basically just the total snowmelt that occurs before the melt onset date, and it's been normalized by the maximum snow depth at each location. And in general, we find across the entire Arctic, on average, for every centimeter of simulated snow on the sea ice, approximately 75% of it will melt by the time that satellite algorithm picks up and it detects continuous melt onset. So this is, of course, only just using one model, but is a really interesting example of how we can also use these more direct comparisons, not only to evaluate climate models, but to inform our process understanding of what observations actually mean. So I think I'm probably over time already, so I'll just leave my conclusions up here, but happy to answer any questions. Thank you.
Thanks, Abby. Are there any questions for Abby? So I have just a very quick one. Are there plans to make this available within the CEIS model, the satellite emulator?
So I have really adapted the input data from the CESM2 to fit within the current existing framework of the simulator, which is publicly available on GitHub, and I can put the link to that in the chat if anyone is interested. Since I've kind of changed gears a little bit, I probably will not be carrying forward the simulator development into the actual CEIS code, but I think there's a lot of opportunity for that, and it would be a really cool advancement.
Yeah, no, it's a great tool to look at this kind of stuff. So thanks, Abby.
You're actually sharing the resultant maps. I just like to see when the predicted earliest sea ice melt is based on old satellite data, so to speak.
Sorry, could you repeat the question? I think maybe I'm.
Yeah, I put in the chat, I would just like to see the output, so you don't have to maintain the code to do that. But like a map which shows when predicted sea ice melting onset is, depending on location, of course.
Yeah,
Or whatever the simulated. And then, of course, I think you said which source of data you used.
Yeah, and so I think right now I've only shown 1 year today. We've done this for 3 years, but there are, we do have ideas and plans to expand it to kind of a multi-decadal time series. And that would be something that we would definitely provide on either the Arctic Data Center or somewhere else to be used by other people.
Do you have, I mean, you said you graduated with your PhD. Is there a map in your PhD? The PhD should be published. The PhD is public always, right? So there should be a page. Perhaps you can send me a link to the page where you have a map of meltpoint onset. Like nothing that should be any work for you.
I'm not sure I'm exactly understanding the question, but yes, the dissertation is published in the full version of the paper draft is in that document, and we're hoping to submit to the cryosphere pretty soon too. I did have maps of the earliest snowmelt dates here, if that's what you were looking for, but there's also, in my past work too, other representations of the melt onset dates derived from algorithms as well, and other people have looked at that too.
So in the interest of time, why don't you guys take this offline and make sure that you guys, get the correct PDF to the correct person. But we need to move on to the next talk. So thanks, Abby. That was great. So now we're going to move on to Chris Wyburn-Powell. And Chris, hopefully you can share your screen. And he's going to be talking about realism of simulated internal variability of CS. Okay, thanks, Chris.
Okay, can you?
We can see it. It's not in presenter or in there. Now it looks great.
Okay, great. Thank you. Yeah, so today I'll be talking about the realism of simulated internal variability of Arctic sea ice. And this is work I've done with my co-authors, Alexandra Yan and Mark England. So the motivation for this work is the fact that internal variability accounts for a very large proportion of the observed decline of Arctic sea ice. But there is a large amount of heterogeneity. So for example, the figure in the top right here shows that in March, there's a very large contribution of internal variability to the ice loss in the Barents Sea. And in September, the shelf seas have a very large contribution as well. But despite the importance of internal variability, we typically only assess model realism on the mean state and the trends. And this is partly because we have different measures of internal variability for models and observations. So the figure on the bottom right here, we have the CSM large ensemble in blue and observations in red. And because we only have one realization of reality, it is hard to use the same methodology to compare observations and models. With the large ensemble, we can easily say that the internal variability can be represented by the spread between these ensemble members. So this is where resampling comes in. So as I was just saying, just using the observations and large ensemble means that we're not really comparing the same thing. We don't have the same ability to look at our single realization of reality with these multiple realizations in a large ensemble. By using resampling, we can use the same methodology for each of the members from a large ensemble and with the observations. And to note here, this still isn't comparing apples with apples because this methodology mainly focuses on the interannual variability, not the low frequency variability, which is the full range of internal variability. So the data sets we use are 6 large ensembles with historical and RCP 8.5 forcing, and these are from a multi-model large ensemble archive. And the 6 models are shown here, and the number of ensemble members are shown in the parentheses. For observations, we use NSIDC and NOAA data, and the time period we're looking at is 1979 to 2020. So the resampling technique we use uses the idea that if we have a time series, the linear trend from that time series can be represented by the forced response, and internal variability is represented by anomalies from that linear trend. So the figure in the bottom left shows the September sea ice area from 1979 to 2020, the gray line showing the linear trend. And then on the right, we have the anomalies from that linear trend representing internal variability. And this is following McKinnon et al. 2017, where they looked at North American surface temperatures. So how we actually do this resampling is that we take a 2-year block bootstrap size and we resample with replacement. So for example, we've taken these anomalies here on the left, and then on the right, we have 2 examples of when we do this resampling. Once we've done this resampling 1,000 times, we can call the output from this a synthetic ensemble. And this basically can be shown in the figure on the bottom right here, where there are 1,000 different evolutions of sea ice, which we determine could have been possible if internal variability were different. And we note here it still has the same trend for all of these evolutions, although the variability year to year is different. And we can do the same thing with resampling for sea ice concentration. And so here we're showing the anomalies from the trend of each of these grid cells for years 96 to 2001, just as an example, where red shows anomalies above trend and blue below trend. So then when we do our resampling, we can show that if we take 2 years at a time, again, we can resample these in many different configurations. But the important thing is we retain the spatial coherence of the grid cell. So each of the patterns is the same. So how do we actually measure internal variability from the models and the observations? So if we look at the standard deviation of large ensemble members, and then we look at the standard deviation of that distribution, shown here in the bottom left for CSM, then this can be our benchmark metric of internal variability. Then when we create our synthetic ensemble of 1,000 resamplings, we can also take the standard deviation across those 1,000 resamplings. So the distribution has a resampling for each individual member. In the middle here, we show member 3 from CSM1. And then when we resample the observations, we also have a standard deviation of that distribution. And so these are the 3 metrics we'll be looking at in the results. So when we look at the Panarctic, we see that resampling captures a majority of the large ensemble spread. So again, now we're looking at the internal variability represented by resampling in the members, and we're comparing that with the large ensemble spread, which is our benchmark for internal variability. So the figure on the right here shows the ratio of that. So values below 1 shows that the large ensemble spread is larger than that which we have recreated with our 1,000 resamplings. And so what's important to note here is that approximately 65 to 90% of the standard deviation of the large ensemble is reproduced when we do our resampling technique. However, it's not 100%, and so we do miss some of the internal variability which is represented in large ensembles. Another thing to note here in the figure is the fact that the shading here represents the interquartile range of the large ensemble members. So it's important to note here that the ratio that we get as a result is highly dependent on the realization which we use. And so in the rest of the results, especially spatially, we'll be looking at the average or the median from these, all of the realizations from the large ensembles.
So Chris, just to let you know, you only have a couple minutes left.
Okay, yeah. I'll go through this quickly. So in conclusion, from the results we have, the For spring, we have much larger internal variability by this metric than the observations, although in September, when we look at the Pan-Arctic, models and observations agree fairly well. We can see that the ratio here is close to 1. When we look at this spatially, we have red here shows higher modeled variability than observations, and blue shows lower modeled variability compared to observations. And so in March, we find that the primary source of overestimation in March is along the Arctic coast and the sea ice edge. In September, we find that there's actually pretty good agreement between models and observations, especially in the South Shelf Sea regions, which is the area where there's the highest variability. So in conclusion here, we have shown that resampling captures a majority of the large ensemble internal variability, allowing more direct comparisons of observations, although this mainly focuses on interannual variability, and there is less low-frequency variability captured with this technique. In general, models simulate larger internal variability than observations when compared with resampling. And in summer, internal variability is modeled relatively well, with the largest overestimation in March due to the sea ice edge and around the coastal regions. Thank you for listening, and I'll take any questions.
Thanks, Chris. Are there any quick questions for Chris? Peter.
Yes, nice talk. How did you come up with the number 1,000 for that resampling, and do the results depend on that number?
Yeah, thank you for the question. So the number of resamplings shouldn't influence the distribution of data we get out. The resampling technique should reproduce, if we have a standard deviation in our data, then the resampling should also produce a normal distribution in our data. 1,000 seems to be a typically used number, which is more than sufficient to accurately reproduce the same distribution of data. And so that was what was used in the McKinnon et al. 2017 paper, and that seems to be consistent across previous research. 1,000 is kind of a conservative number to make sure that that is a robust way of measuring it.
Thanks, Chris. Okay. So if you have any other questions for Chris, please put them in the chat. And we'll move on to our next talk, which is from Alice DeVivier, talking about impacts of sea ice mushy thermodynamics in Antarctic simulations.
Great.
And it looks great, Alice.
Okay, great, thanks. Let me just move all the pictures so I can see the time. Okay, so the purpose of this experiment, or what I'm going to talk to you about today, is we wanted to further explore impacts of sea ice thermodynamics in the coupled system. If people were at the Polar Climate Working Group in meeting in February, I talked about this some, so this is a bit of a conclusion from that. Okay. All right, so I think Chris and I were looking at the same graphics about apples and oranges, but just to give you a little summary of what we found here, Hansi's paper on analyzing the CESM2 experiment found that while the sea ice state was not super different in the Antarctic, we found that there were big differences in the frazzle ice production. So hopefully you can see my mouse here, but you can see there's like a ring of fire around the coast of Antarctica, but that's not actually volcanism, that's frazzle ice production, or production of ice in open ocean waters. And that was not present in CESM1. And so one of the big questions is, why does this exist? And one of the immediate culprits is that CESM2 uses this new sea ice thermodynamics that we call the mushy layer thermodynamics, developed by Adrian Turner, where there's prognostic sea ice salinity, and the ice is a combination of like mushy solid ice, and it's a mushy combination of solid ice and brine. In contrast, CESM1 uses the Bits and Lipscomb 99 thermodynamics, where the salinity is not prognostic. But there are a ton of other differences between these two models, so we wanted to be able to compare more apples to apples, again, looking up similar graphics. So what we did is we ran 2 CESM2 experiments where the only thing we changed was the sea ice thermodynamics. So one of these uses the Bits and Lipscomb 99, and one of these uses Mushy. They're both pre-industrial experiments. They're 100 years. Daily and monthly data are available. I'm going to show you figures that use the monthly data, and Dave has done some similar analysis in the Arctic. I'm going to focus on the coastal regions, and I'm also going to focus on the Antarctic winter. So this is very similar to the plot that I showed from Hansi's paper, looking at the Frazel ice differences. So I want to point out these are all differences. And where there's stippling, that means that the difference is not statistically different. So what I want to point out is that where you see the biggest differences in Frazel ice production are right here along the coast. And this area, this coastal area, accounts for about 56% of the total thermodynamic sea ice growth in the winter in the Antarctic. So this is one of the reasons I'm focusing on what's happening on the coast. When we look at the coastal ice mass budget throughout the year, we're looking at this figure. I want you just to focus on the net budget, the net thermodynamic terms, and then the dynamic terms. So those are the colors here. I just want to point out that there are significant increases in the thermodynamic growth. So this gray line right here, in all months, the little diamonds indicate that the difference is significant. So throughout the whole throughout the whole growth season, there's an increase in thermodynamic growth in the Mushy experiment. Again, I'm showing differences here. And but that is somewhat compensated by an increase in dynamic loss. So that's what we're seeing right here. And so on the whole, the net budget is not very different. It's a little different at the beginning of the melt season, or at the beginning of the growth season, sorry. And then it becomes not statistically significant differences. So what we're really interested in is what this does to the ocean and the atmosphere around Antarctica. So what I'm showing here is a cross section averaged across this Adventine-Bellinghausen Sea sector. That's the star here. And what we see is that when we look vertically, so the y-axis here is depth through the ocean ocean water has become more saline. In the Mushy experiment, again, these are differences, Mushy minus Bits and Lipscomb 99. And so we find that originating at the surface where the sea ice is forming, the ocean is becoming denser. And this is true in all the sectors. So I'm just showing the cross section here for the Adventine-Bellinghausen Sea, but you can look when we just look at 100-meter depth, that there are increases in density almost everywhere. So that's the red colors. And when we look at the changes in salinity, we see that there are increases in salinity pretty much everywhere in all the sectors as well. And they vary, the spatial pattern is very similar to what we see for the density itself. This is a reflection of the increase in thermodynamic growth in these coastal regions in the Mushy experiment. So in CESM2, when ice is formed, fresh water is basically removed from the ocean, and so the ocean will become more saline. And that the changes in temperature, which is what I'm showing here in the far right column, are not significantly contributing to these changes in density, and they're not consistent necessarily with depth or by sector. So why this is relevant is that it impacts the overturning it impacts the meridional overturning circulation. So what you can see here is just the annual mean of the MOC for the Mushy experiment. So we have the upwelling kind of water here and then downwelling here. And when we look at the difference, we can see there are significant decreases here in the Mushy experiment of the overturning at lower densities. This is density space here. And then we have increases at higher densities. And so what that looks like when we look at a time series over the whole 100-year experiments is that this dark line is the 10-year running mean, but the Antarctic bottom water production is like slightly higher, but the difference is significant through pretty much the entire 100 years with the Mushy experiment compared to the Bits and Lipscomb. So basically the volumetric flow rate has increased for these higher densities. The higher densities exist because we're making more ice and getting saltier, denser water. I told you that I would talk a little bit about what's happening in the atmosphere. The short answer is much less. when we look at differences in the sea level pressure, they're insignificant pretty much everywhere. So there's not really any significant circulation change. There are small differences in the precipitation, but they're not consistent by sector, and they don't seem to be driving any of the changes in snow ice formation. That's related to the thermodynamics as well, the mushy thermodynamics. We do find that there's a slight decrease in the cloudiness around Antarctica, but it's very small. And even though it's significant, it's not a huge difference. So I know I'm almost done with my time here, Marika, you don't have to remind me, but where this is going now is what I'm working on at this, the newest work that I've been doing is using machine learning or self-organizing maps with some of the CESM2 output to try to understand the processes driving these polynyas or open ocean areas around the coast. I'm looking in more regional areas, and I'm trying to understand if what's changing that, what's driving the polynyas changes over time, and if that might change into the future. So I'm just showing, this is very much in progress, but a SOM that's trained with sea ice thickness in the Ross Sea, and you can see just the coastal sea ice thickness. There's some times where it finds there's, very little, very thin ice around the Ross Sea, and we know that a polynya occurs here. So it's basically identifying that polynya. All this black is just data that we didn't use to train. So I think with that, I'm done, and I can go ahead and take any questions if we have time.
Great, thanks, Alice. I think we have time for a question. So Gokhan, I see your hands up.
Yeah, I had a quick question. Which one is more realistic, I guess, CSM1 or CSM2 with mushy layer physics? And can the mushy layer parameterization or parameter values be adjusted to produce similar results, I guess? How much freedom is there?
So I would say that the mushy layer is more consistent with how the sea ice itself evolves in time. So I think that I would say that maybe that one is more realistic. I haven't done a close comparison. I've tried to find observations of ice density and ice temperature, throughout the ice in the Antarctic, and those don't really exist. So it's hard to say it's getting it spot on or something like that. But I do think the prognostic salinity evaluation or evolution, is more realistic with what actually happens in sea ice.
I guess my question was, yes, it's more realistic physics, but is it producing more realistic simulations? I guess that's what
I think the mean sea ice state was better in CESM2 than it was in CESM1. So in that sense, I think yes, but I think it depends how you define better, probably. There are probably measures in which it's not as good.
Thank you.
There's a caveat too that we're not doing true salt flux coupling. We're still assuming 4 PSU. And so that's one of the things I'm working on fixing.
So we have several more questions and we don't have a lot of time. So I'm gonna let Cece go, but then Bob Hallberg, I see you raised your hand also, if you could put that in the chat for Alice. So Cece, can't be long though. You're eating into your own time.
I know, it's a technical question too. Good, neat talk, Alice. So good to see this work done. And I'm curious if you thought about trying to adjust the fixed salinity profile in the Witz and Lipscomb model to something more like a saline fresh ice distribution or profile, because currently it's very fresh at the surface.
Yeah, I have thought about that and how you and Bill, I guess, decided on the profile you use. I have not done experiments where I did adjust that, because part of the purpose of these of this analysis is just to understand, try to better understand why we're seeing the differences we do. So again, trying to keep apples to apples or oranges or whatever fruit we have of the day, that evaluation more consistent. I think, one of the things we saw was there were differences in the overturning in Antarctic bottom water formation in CESM2. And so that was another one of the motivations, is to understand, is this being caused by the thermodynamics or other things going on? And so then if we wanted to see how it was different from CESM1, I wanted to keep the same profile that you guys had used. But that is something we could do, try to make it more similar to mushy, because the ice profiles are very different. The salinity profiles. All right, I'll answer the other questions in the chat. Thank you, everyone.
Thanks, Alice. Okay, so now we're on to the last talk of this session, which is from Cecilia Bitz, talking about a machine learning model of sea ice in the Arctic.
Great, thank you. I don't know how I just got off onto the wrong slide. Good. Somehow I managed to forget the last word on my title in the when I applied to give this talk. So it really should be of sea ice velocity exclusively. And this is really largely the work of June Zhai and myself at University of Washington. So I'm going to acknowledge her vast contribution to this work. And what we're interested in is, can we actually avoid a model like a dynamical model and instead use a machine learned model of sea ice motion to make a superior forecast? And by that I mean kind of what the next time step forecast of sea ice motion is. So why we might hope to do this is that the sea ice motion field is very complex, and there are lots of sophisticated dynamics that go into the dynamical model computation of things that could cause it to kind of lock up at the ice edge and exhibit complex dynamical behaviors. And it's questionable whether we actually know the right physics. I think we obviously have the right momentum equation for F equals ma, but it's this interaction of ice with itself that is uncertain, and it's really largely in models based on kind of rules of what we think are the material relationships of sea ice, specifically the stress to the strain rate, or possibly other scalars that dictate this ice material property. So let's just see if we can avoid all that and go right ahead and calculate the ice motion field with a statistical model. And I think this might be a good example of a test problem for this kind of work, because there's such a wide range of sea ice concentration seasonally. So we really have this wide range of data from which to train our model. And the basic method we're going to use is to train our statistical models with the sea ice concentration at one time step 0, and the ice motion at that time step as well, for both U and V components of the ice velocity. And then we're going to include the winds of the current time that we're interested in forecasting. So we assume that we know the wind, but we don't know the ice motion and concentration also. So that's our basic model. And the time step I'm going to propose is 1 day, and that's because the ice velocity data that we have is available only once daily. But we first started this whole exercise with using ice motion output from CESM2, as well as the concentration and thickness. So in this case, we actually threw in a predictor of thickness. And again, all of these are at the initial time step, and we're trying to predict at time step 1. We assume we know the winds at that time step. So we tried various models built on these predictors. And the method I'm showing results for here is a convolutional neural network to just show you what kinds of statistics, and these are our skill statistics, the correlation or anomaly correlation coefficient, and 1 minus a normalized root mean square error. And you can see actually they don't vary a ton, which is good news. And that really means, hey, we can probably just chuck the thickness, which is great because obviously we don't observe the thickness very well. So in fact, we decided we would use this set of variables, which was the one I showed on the previous slide. And basically, the lesson here is that ice motion or winds, ice motion from the previous step or winds of the current step are good predictors themselves, which is a very fortunate situation to be in. And the metric, or the time step here was 1 hour, but if we shrunk it down to 1 day, it actually increased the skill. So that's nice too. So just to show you a whole range of models to begin with, compared to the truth here, which is a satellite-based observation from the Polar Pathfinder primarily, compared to a convolutional neural net, the dynamical model CEIS at 1 degree resolution, another machine learned model, multi-layer perceptron, a random forest machine learned model, and then just a simple linear regression. And obviously all of them look pretty good, but they do differ in some qualities, such as statistically, I'll show you in a minute, but for this just one random day, you can kind of get the sense that size looks like it's too strong, and the pattern looks good. And then the random forest tends to be a little bit kind of erratic. Linear regression is a little too smooth. So let's just go and now look at some actual comprehensive statistics for all of 1 year of training data. So this is for year 2015. I should say we trained the model on something like 1990 to 2014, so something like 25 years of training data. And what we found for this correlation statistic, it is like an anomaly correlation coefficient, where X is the truth and Y is the model. And you're looking at basically the correlation between the two in a pattern, and then summing over all locations in space. And we did this for U and V separately, and just sort of made one large vector for the index I here. And what we see is they're all pretty good, but size maybe for this group is of interest. It's kind of in the middle of the pack. So that's kind of neat that we can do pretty well with statistics compared to our familiar size 5 dynamical model that is already in CESM2. I should say we're forcing the size here with the same reanalysis product that we used for the wins in our models that are statistical based. The other skill score I used here is more like the normalized root mean square error that I had on the previous slide. I apologize for changing my name of this variable, or this metric. It's a ratio of standard deviations, and that's quite a bit harder metric to look successful at, especially if the magnitudes are slightly different. And that's where size looks poor, and that's because according to this version of truth that we've used, it overestimates the magnitude size does compared to the truth. So I think probably we ought to redo this with buoy data, which would be an independent source of observations from the training data set. Obviously, we separated in time our testing and training data, but it's still the same basic the same basic data set, right? It's all polar pathfinders. But if we used an independent data set, like the raw buoy data, we expect these results could change a little bit. So that's something we're working on next. But I do want to, before I end, show you a picture of the spatial pattern. And the success of the convolutional neural network is really greatest in the central Arctic. And it is worst right along the coast and along the ice edge. And the same is true for the SICE model, as well as virtually every other machine learning or linear regression model. That the places that they have the kind of biggest struggle with accuracy is in these coastal regions and along the ice edge. So now I'll just say, well, what's next is to try to do this comparison to a high resolution SICE version to, like I said, evaluate the methods against buoy data alone, evaluate things like divergence and shear. We'd really love to implement this machine learning method within SICE instead of, so it's basically strip out the dynamical model and input a machine learning model, because it should speed up the code significantly and maybe increase the accuracy. But I've been really eager to try to learn actually the stress to strain relation itself instead of doing the ice motion directly. So with that, I'll just end and take questions while leaving up my conclusions.
Great, thanks, Cece. So it looks like Gökhan has a question.
Yeah, just hopefully a quick question. Have you, I mean, given that there's, you considered like 5 methods, have you considered looking at the skill as a multi-method average or ensemble, rather than just solely focusing on machine learning? Because if you combine them, it looked like the end result might be a lot better.
Hadn't thought of that. It's a cool idea. Because my motivation obviously was to actually eliminate the dynamical model inside in a climate model. It wasn't really on my radar, but I think that's a cool idea. Thanks.
Thank you.
Do you think just putting linear regression in would be, I mean, it's almost as good as the very complicated neural net. So, I mean, it would be very simple to add a linear regression into SICE instead of the whole neural net.
Interesting point. And yeah, the marginal improvement isn't that great. So maybe it's worth just going with linear. It certainly would be simple. Though it's not that hard actually to implement swanky neural network models either. It's just more black boxy. Yeah.
So Bob, so we are going to eat into our break in just we don't have a break anymore. So I'll let Bob go, and then we're going to take a 1-minute break and come back for the next session.
Thanks, Cecilia. One of the challenges with kind of machine learning is anytime you get outside of the training part of parameter space, things can go badly wrong. Is there any indication from any experiments that you've done that that may be an issue here as well, and one in favor of using a dynamical model?
Great question. And I started by bragging about how this might be the perfect data problem because we have such a wide range of CS coverage over the seasonal cycle. So we do really have this large amount of range of data to train on. Another point, though, is that the ice velocity hasn't changed very much over the observational record. There has been some claim that it's sped up a little bit. I think we don't really see that evidence very strongly. It's certainly not large compared to the noise. So I appreciate your question, and I don't have an answer other than to say this might be a particular problem that is less of an issue. Thanks.
Okay, so I think there may have been some more questions. So if you have other questions for Cece, if you could put them in the chat. And because we ate into our break really effectively, we were supposed to have 10 minutes. We don't have any time at all. Why don't we come back at 11:05? Is that okay, Jan, as the next convener? Okay.
Yeah, absolutely, because we have one presenter who canceled at the last moment, so we have a little bit of room. So let's take a 5-minute break and start at 11:05 with Laura. Thank you.
Thanks. So Cece, you're taking on the whole sea ice dynamics community.
Oh.
All we need is a neural net. We're fine. We don't need that complicated ice dynamics.
Yeah. It was just really a fun project for us to learn about machine learning, and kind of chosen because it doesn't seem to have some of the challenges like Bob Halberg was mentioning.
Yeah, no, it's very interesting. I mean, yeah. How updated is the Polar Pathfinder data? I mean, I guess like if you were doing this in practice and trying to do a forecast for the next day, is that problematic that like the ice motion data is not available at, at near real time?
Yes, I don't think it's available. If Walt is here, he'll be able to say. So we hadn't really thought of this as a forecast. So I use the term forecast with reluctance. It's not really meant to be an operational forecast. It was meant to be a forecast within a climate model. So a forecast of a time step. So that's why the goal for me was to swap it out for the dynamical scheme in a climate model. So you think of the time stepping of solving a differential equation as a forecast.
It'd be interesting to see how quickly it goes wrong. I mean, because it's all based on knowing the information today to predict the information tomorrow. So if you were doing that sequentially in a climate model, like do the errors grow to the point where, a month out, your forecast is crummy?
Good question. And I think if we didn't have the winds as a strong driver, it's very likely. But the winds are a strong driver. Really?
Right. I mean, yeah, that's not surprising, right? It's the biggest term in the momentum budget, the wind storm. So
yeah. So
okay, let's move to our last block of our session with 2 more speakers, and then we have our awesome breakout sessions following those. So we have 2 more speakers focused on land ice, and the first speaker is Laura Muntjev. Laura, I think now you can go ahead and share your screen and unmute yourself. There you are.
Yes. So let me just.
Yeah, and if you go into some sort of full screen mode.
Let me see. Is this full screen mode?
No.
No.
It should be somewhere in your view. Let's see what it looks like for me. View and then full screen mode.
Here we are.
I still don't see it.
You don't see it? Oh, I see it.
So if you unshare and then share your full screen instead, does that work? Or try again.
Like this?
Yep.
Yeah.
This looks great.
All right.
Go ahead, Laura. You have 8 minutes.
Yes, perfect. Thank you. Well, good morning to you. For me here, it's evening. My name is Laura. I work at the TU Delft in the Netherlands, and I will present to you some work that I did on the Greenland ice sheet surface energy balance. It's a spatial analysis in a warming scenario. And for this, we use the CESM model that is coupled to the CESM tool with interactive Greenland ice sheet dynamics. We recently had a paper out describing this coupling with many people of the Land Ice Working Group contributing there. The coupling, it consists of dynamic ice sheet margins, which communicate to CLM, dynamic ice sheet topography communicating to COM, and of course we have a physics-based surface energy balance calculation with elevation classes in CLM, and there's freshwater fluxes to POP. The simulation that I'm using is an idealized simulation, a 1% simulation. It starts at the pre-industrial values of CO2, and we increase it 1% every year until quadrupling in year 140, which is about the same atmospheric value of CO2 that the SSP 8.5 scenario reaches in 2100. So in that sense, it's a nicely comparable pace of that. And for the remainder of the simulation, which is another 210 years, we maintain the 4 times CO2 levels. And here I will focus on 2 periods of analysis, which is around the quadrupling period here in the blue shade, and at the end of the simulation, the 20-year average. And the results are the ice sheet is losing mass, of course, in this warming scenario. The graph here depicts the black line. The mass balance is going down, and it's mainly dictated by the surface mass loss and not so much by ice discharge or the basal mass balance. And it seems that like the surface mass balance is mainly dictated by the melt acceleration. And now our question is, where does the melt energy come from? And we're going to look at the surface energy balance, which is the available melt at the surface, the sum of the net radiation from long wave and short wave, and the surface heat fluxes, which are the sensible latent and ground heat flux. And of course, I cannot cover this all, so I'll just give you a quick overview what happens here, and then pick 2 topics that I will elaborate on a little bit more. So what happens? The melt energy increases a lot. And the main source initially is the long wave radiation. So at stabilization time, 40% of the additional melt energy comes from additional long wave. So mainly, of course, long wave downwelling from the greenhouse gases in the atmosphere. And then after this, at some point, the ice albedo feedback is triggered because snow cover is lost and bare ice is exposed. And more additional radiation comes from the shortwave radiation at the surface. Yeah, more. So at stabilization time, we have about 10 centimeters of sea level equivalent that the Greenland ice sheet has lost. And at the end of the simulation, it's more than a meter, which is, we have 8.5 kelvins of warming. So for the results, I will pick two parts to talk about some more. One is the cloud radiative forcing, and the other one is the ground heat flux. So the cloud radiative forcing we have defined. So shortwave clouds are known to reflect radiation, defined as the shortwave net radiation at the top of the atmosphere minus the shortwave net radiation in clear sky conditions. So this is usually a negative quantity, and cooling. And long wave radiation we define as the outgoing long wave radiation in clear sky conditions at the top of the atmosphere minus the outgoing long wave, normal outgoing long wave at the top of the atmosphere. And usually this is a positive quantity as it's remitting the long wave radiation. So what's it doing here at the bottom? I included 2 graphs of Greenland ice sheet integrated values. The shortwave cloud forcing, it is negative, it's cooling, and we find that as the climate's warming, the cooling is increasing of a few watts per square meter. The top panels here, the top spatial panels, they show the first one is the pre-industrial average, the middle one is the around stabilization, so between so around year 140, and the last one is at the end of the simulation. We see that the most clouds cooling in the shortwave is in the ablation zone. The red line is the equilibrium line altitude, and as that shifts up more cooling is also realized there from clouds. The long wave cloud radiative forcing is changing very little and not significant at all. And it's interesting to see that if I add them up together to find the total cloud radiative forcing, it's a positive quantity. So in the pre-industrial time, clouds are warming the Greenland ice sheet slightly with a few watts per square meters. These is the bottom row 3 maps, and the brown contour is the 0 contour. And as the climate is warming, we see that it's switching signs, and at the end of the simulation, there's net cooling. on the ice sheet, except for this small area here in the highly elevated area in the east. And the other thing I wanted to talk with you about is the ground heat flux. So the ground heat flux we have defined as on the interface between the atmosphere and the land. So this is also including the snow. So it would be an energy flux of heat transfer, can be into the snowpack or out. It's a generally small component of the surface energy balance compared to, of course, the radiative fluxes and also the turbulent fluxes. But it's interesting to see what's happening in this multi-decadal and centennial time scale. In the pre-industrial time, we see that it's a positive. So again, it's a positive defined as contributing to the surface energy balance, and negative it's withdrawing energy from the surface energy balance. It's positive here around the south in the ablation zone and around the equilibrium line altitude. And as the climate warms and the equilibrium line altitude, also the area where the ground heat flux is positive is increasing. And we spent some time on thinking what this means, the heat conduction towards the surface from out of the snowpack. And we reckon that it's releasing energy that got into the snowpack earlier from latent heat releases of refreezing melt energy. I'm sorry, of refreezing meltwater. So in essence, it's preparing the snowpack for a full melt. Another interesting feature.
1 minute, Laura.
1 minute, yes, almost done. Another interesting feature is if I compare these maps of the ground heat flux to the refreezing maps, we find there's also refreezing in the north, but not so much a positive ground heat flux there. And we reckon that the North snowpack has sufficient cold content to buffer such heat releases of the melt, and therefore it's much more stable there. So that's what that was for my points. So the clouds have initially a warming effect on the ice sheet. As the climate warms, clouds become to have a cooling effect, which is due to more cloud reflection in the shortwave radiation. And the ground heat flux, it's bringing refreezing energy to the surface of prior meltwater that is refrozing in the snowpack. Yeah, that's what was my presentation. If you have any questions, I'll be happy to address them.
Thank you so much, Laura, and thank you for staying up this relatively late hour for you.
No, it's not late.
Any questions for Laura? Please raise your hand or type them in the chat.
Should I stop sharing, Jan?
Yeah, you can keep these slides, this slide on for a little while, so people can take a look at them and try to remember this. So I have a quick question for you, Laura, if no one else has one. So you mentioned the net cooling effect by clouds, but basically everywhere, especially or except for an area on the eastern side of the Greenland ice sheet. Did I understand that correctly? And if so, do you know why that particular area is not seeing the cloud cooling effect?
Well, I'm not really sure, and I've been thinking about my definition of the shortwave cloud forcing actually a bit recently. So that's also why I am presenting this. Then I'm thinking maybe I'm including the effects of surface albedo change and attributing them to the cloud change. So that might be a reason. And of course, in the east, it's very high and elevated. I imagine that's not so much the albedo, it's changing there. If that does make any sense to you.
Yeah, absolutely. Okay, if we don't have any more questions, Laura, please stop sharing your screen and I can give the virtual floor to Ravindra. Ravindra, please start sharing if you're ready. If there are any more questions for Laura, please type them in the chat and she can answer them right now. And Ravindra, please go ahead. This looks good. 8 minutes. I don't hear you, Ravindra. I think you're still muted.
I think now you can hear me, right?
Yep, perfect.
Yeah, the screen disappeared, sorry. All right, good morning, everyone. My name is Ravindra Dudu. I'm an associate professor at Civil and Environmental Engineering at Vanderbilt. That's a recent change. And for the past few years, I've been working on damage mechanics formulations for calving. And I've always been presenting work that is outside of CESM. And so I'll guess continue that tradition even today. This is my way of reaching out to the community and getting feedback and trying to eventually work with CESM. This work is done in collaboration with Alex Huth, who is now at Princeton, and Ben Smith, who's at University of Washington. And we have NSF grant and a new NASA grant that I want to acknowledge the support of. Ice shelf fracture and iceberg calving accelerate ice sheet mass loss. As you can see here, the Larsen B ice shelf collapse apparently accelerated the ground ice flow behind the ice shelf from the collapse. And also Larsen C ice shelf calving that happened in 2017, calved on a big iceberg, A68. And overall, the main point that I want to mention is that ice shelf fracture is poorly understood and it's poorly represented in ice sheet models, right? And there is also this other complication of atmospheric warming due to which a hydrofracture, and I lose that in a loose way, can be a factor too. So, so go ahead. Yeah, sorry about that. So mainly when you look at ice sheet models, the way calving mass loss or the calving front motion due to calving mass loss is modeled is through a continuous process. And on the left here, I have a paper by Bonzio and it involves Helen Surus and Matthew Murligam and Eric LaRue. And they're using a level set method to gradually move that calving front, right? So they will have some kind of velocity parameterization for that calving front. And then over time, it gradually moves like a continuous process, right? However, on the other end, or on the other side, I want to focus that, you know, there are these fractures, which are really discrete features on the ice shelves. And when, of course, calving happens, you have discrete events where icebergs are separating, and that can contribute to a huge loss in the ice extent, right, or the ice shelf extent. And you cannot really handle that as a continuous process. And then, especially if the meltwater-driven fracture makes calving more plausible, right, or possible rather, then you really have to have a method to handle this. So that has been our motivation. And I'll just play a video. I don't know, I don't think this is playing, right? It's not showing. I think I have some kind of a bug because of which the video that is not showing. Sorry about that. But what we have been developing is a generalized interpolation material point method, and the CIS community has started using these sorts of method first. In fact, Elizabeth and CC must have pioneered some of these works. And we have, for the first time, adapted that to Glacier. I'm sorry, this video doesn't seem to be playing right now for me. But we have a new paper that just got accepted a few weeks ago, where we described how this method can be used for shallow ice shelves. And we have shown that we can even add the thickness evolution. And the way that whole process worked along with calving now, which we have incorporated, is through flow work as follows. So we first solved this shallow shelf approximation, which is a depth integrated model. Then from that, we get the velocity. And once we get the velocity, we can get the deviatoric stress through the standard Glenslaw type constitutive model. Then we assume that we know the pressure based on the assumption that the vertical stress is hydrostatic. And once we have that, then we implement, if you look at the bottom right-hand corner, we implement this creep damage evolution law. And in that, we can even parameterize the presence of water and the hydrofracture parameterization, if you may call that. And the creep damage is done through a separate subroutine that gives in a quasi 3D approach, what is the depth to which the crevasse will propagate. And then we now get those crevasse propagation profiles, which is shown in this bottom left figure. And from that, we depth integrate to extract the damage, which then goes into the shallow ice shelf formulation. So that's, and then we do this using a certain time step. The time step is typically smaller than what you would run without damage. So that is a limitation. To go over quickly what the equations are, on the left-hand side, you have these vertically integrated momentum balance. The bottom equation where I showed the deviatoric and pressure is the new sort of addition where we put PW, which is a hydrofracture or parameterization from seawater in basal crevasses. And then we evolved damage through something called a Hayhurst criterion that captures brittle and ductile fracture in a very empirical way. And finally, the last equation on the right-hand bottom is the depth average damage tensor, which then goes to affect the viscosity in the vertically integrated momentum balance equation, right? And we described this whole method in a paper in James that just is tentatively accepted. So we have two papers that are coming out in James as part 1 and part 2. Then just to show a few pictures of what can be done, we did the MISMIP plus example. We got calving profiles due to the damage that look like a curved fracture pad that fully propagates. That sort of reminds us of the Pine Island Glacier fracture. So that's one thing. We also applied it to Larsen sea ice shelf. This is something we are currently working on to tune the model and to conduct parametric sensitivity. And in one of the tuning cases, we were able to reasonably capture the calving that happened after 2.2 years with so the time doesn't match very well, but we can match the fracture path, and which is evident from this yellow dashed line, which is observations, and the red one, which is our model prediction. And finally, we also developed a new damage law that can capture crevasse propagation in a consistent way. I'll move on to the next slide in the interest of time, but here, hopefully this movie will play and we can actually simulate this sort of marine ice cliff failure due to shear. And so we were looking at can crevasses progressively fracture at the terminus of a grounded glacier or a marine ice cliff, and eventually cause a mass loss that keeps progressively moving inland. And we do see some evidence of that happening, and particularly the shear stress, which is in the left figure in the subfigure C, seems to drive this kind of calving or fracture process near the terminus. And so that's what this work that came out in Extreme Mechanics Letters early this year showed. And so we had a good year. 3 papers accepted or published. So with that, I'll stop. And the 2 conclusions are that the material point method can be useful for shallow shelf approximations in modeling this discrete fracture process in ice shelves. And so I think that should be a valuable addition to CESM. We have to work on that. And then anisotropic damage models and tuning to observations is something our future work is tackling. Thank you.
Thank you so much, Ravindra. In the interest of time, unfortunately, there is not much time for questions. So I would suggest everyone who has questions for Ravindra to put them in the chat. In the meantime, it's almost 11:30. Anyway, so we are ready. We should be ready for the breakout rooms. I think Todd prepared them.
They are ready.
Okay, so Todd, please launch them. And you can choose your favorite breakout room, and each of the breakout rooms will have conveners. So please pick your favorite topic, and we will be in the breakout rooms for probably something like 25 minutes or so, and then come back all together just before noon to wrap up. And then at noon, we will have 2 new breakout rooms, one for the polar climate, one for the land ice working group, for an informal lunch. And there will be 2 more if people want to, discuss something very specific. But more on that later. So if you're ready for a breakout room, please pick your favorite one. There we go. And we'll see all of you back in 25 minutes. More information will be given to you in the specific breakout room. Enjoy.
And once you're in the room, you can open the breakout room menu and press join on another room. Please let me know if anyone needs help entering the breakout rooms.
Actually, yes. Can you repeat the directions?
Yeah, sure. Press the breakout room button down the bottom.
Mm-hmm.
And then you should see a list of the rooms, and there's a blue join button on the right.
Got it. Thanks.
Okay. Please let me know if anyone needs help joining a breakout room. Hello, people are in breakout rooms now. You're welcome to join one.
Hi, everyone. I guess we're all coming back to the main room now. So hopefully the breakout groups worked well. We were having a good discussion in the CIS prediction group, and of course got cut off, which is, I guess, what happens when you're in breakout groups and get kicked out. So, so I think in terms of wrapping up, you know, we have all the talks and things like that will be recorded, available online. So if you missed something, please go back and take a look. Hopefully this sparked some conversations and opportunities for collaboration. And so, you know, I definitely would encourage you to follow up on those things. Right now, we actually are going to move into sort of these informal lunches, and I think we'll have breakout rooms set up for that. And so if you're available to join for lunch, it's going to be just very informal, just a way to kind of chat and check in. And so please join us for lunch if you're available. And, you know, I think we had a lot of really great science presented. It's just wonderful to see the breadth of things people are doing across the polar climate and the land ice working groups. And it's just really exciting stuff. So thank you to those of you who presented. I don't know if my fellow co-chairs, Hansi, Jan, Bill, or the liaisons, Gunter and Dave, want to add anything. I just kind of took over. But
just to say thank you to everybody, because this was a great session. So,
and please,
thanks everyone.
Hopefully we'll see you in person soon.
Yeah, hopefully we see a lot of you at lunch. And hopefully we see you in person at winter meetings at NCAR. So,
Marika, could you remind us how we join a breakout for lunch? Like if we want to join the land ice conversation or the polar climate conversation? So
they're in your, down at the bottom of your Zoom screen, there's breakout rooms. And if you click on that, there's at the very bottom, you'll see everybody's names. At the very bottom, there's the Land Ice Working Group lunch table and the Polar Climate Working Group lunch table. You can, on the right of the panel, you can click on that to join. We also did put together 2 open rooms, partly because we saw that in the chat, there were some people saying, oh, we should discuss this later, or, oh, it'd be great to talk more about this. And so we left 2 rooms open. So if there's groups of people that want to just go to one of those open rooms and chat about something that came up during the meeting, you're welcome to do that. So basically, that's how you join one of these lunches. I'm going to take a 5-minute break or so. And yeah. So I'm expecting that we'll join these lunch tables, but it might actually be 5-10 minutes before people are actually there. And please grab lunch if you want and bring it back. But yeah, so that's how you join. And if things come up, you want more information on simulations, or as Hansi said, you need to use your computing time, Polar Climate Working Group people, please contact us if you need help with that, because we don't want to lose these computing resources. And we've got a lot of great things that people proposed. So with that, I guess we'll just close the meeting and please join us for lunch.
I have one more thing. I just want to thank Todd Amadeo for supporting our meeting so capably. And, yeah. and we've had great support also from Elizabeth and Stephanie. And so when you see these folks, please tell them you appreciate what a great job they've done.
Yeah, and Ryan as well.
Ryan as well.
Yeah, so thanks.
Thanks, Bill.
Yeah. Okay, well, hopefully we see you at lunch. And thanks for a great meeting. It's been really good to see everybody's work.